What if everything we know about the universe is merely the opening chapter of a much grander narrative? As humanity ventures deeper into the cosmos, we find ourselves confronted with enigmas that not only challenge our comprehension, but also spark our imaginations. This ongoing exploration leads us through the vast corridors of space, revealing the hidden inheritance of the universe, its expansive history, stunning galactic phenomena, and the elusive cosmic signals that might point to life beyond our own planet. As we peer into the cosmic abyss, those who dare to reach the farthest corners of the universe are greeted by a breathtaking tapestry of wonders. The edge of the universe, often seen as the limit of our observational abilities, offers glimpses of phenomena that could serve as keys to understanding the origin and evolution of everything. Perhaps the most remarkable of these features is the cosmic microwave background radiation, a faint glow that permeates the entire universe. This radiation is the leftover energy from the Big Bang, the hot, dense era that birthed the universe approximately 13.8 billion years ago. It serves as a relic from the very beginning of time, illuminating the infancy of our cosmos. As we extend our gaze further into the universe, we encounter distant galaxies, vast collections of stars, gas, and dust. These ancient galaxies appear in various stages of their development, offering a live window into the evolution of stellar systems over billions of years. Through the lens of powerful telescopes, we don't simply see light, we are witnessing history itself. The formation and merger of stars, the birth of stellar clusters, and the dynamic processes that have shaped the universe as we know it all come to life before our eyes. Some of the most distant galaxies we observe today are only a few 100 million years old, a mere blink in the timeline of the cosmos. Among the most captivating sights in this far-flung realm are gamma-ray bursts, explosions of unimaginable energy. These bursts are among the most intense events in the universe, often marking the death throes of massive stars or the violent collision of neutron stars. These cosmic explosions offer tantalizing insights into the extreme physics that govern the universe, shedding light on the processes behind stellar evolution and the creation of elements essential for life itself. By studying these bursts, astronomers can probe the fundamental forces that shape everything from the smallest atoms to the largest galactic structures. Yet, as we push further into the depths of space, we are confronted with an unsettling realization. The universe's boundaries are not clearly defined. The more we observe, the more questions arise, leading to new discoveries that defy easy answers. Each new observation fills in a tiny piece of the puzzle of the universe's history, while simultaneously raising even deeper questions about what lies beyond our observational reach. It's as if the more we uncover, the more we are beckoned to look further into the cosmic expanse. The edge of the universe, then, is not simply a limit, but rather a doorway, an invitation to explore the unfathomable vastness that remains hidden from our view. Understanding this boundary is one of the most captivating challenges in modern cosmology. Scientists begin their quest by studying what is known as the observable universe. This refers to all the celestial objects and light we can detect with our instruments, stretching across a vast 93 billion light years from Earth. But even this seemingly boundless realm is not a physical boundary, and instead it marks the limit of what we can currently see. Anything beyond this distance has not yet had enough time to reach us, given the age of the universe since the Big Bang. What lies beyond this observable horizon remains one of the greatest mysteries of all. Some theories suggest that the universe extends infinitely beyond our perception, a vast, unseen expanse filled with galaxies, cosmic structures, and phenomena we can only dream of understanding. Could there be an infinite number of stars, galaxies, and even life forms just beyond our reach, waiting to be discovered? Or is the universe finite, with a definitive edge that we are simply unable to perceive? These are questions that continue to tantalize scientists, philosophers, and dreamers alike, driving our relentless search for knowledge. As we continue our journey into the universe's uncharted depths, we are reminded of the vastness of our ignorance and the infinite possibilities that lie beyond. The more we explore, the more we realize that the story of the universe is far from complete. It is a tale still being written, one discovery at a time, as we push the boundaries of our understanding and reach for the stars. And perhaps just as we peer into the endless expanse of space, we might also be looking into the very nature of existence itself. Furthermore, other hypotheses suggest that the universe could possess a curved structure, possibly allowing for a finite volume, yet without any traditional boundary. This concept is similar to the surface of a sphere, where traveling in one direction could eventually lead you back to your original starting point. This idea challenges our understanding of space and shape, opening up the mind to the possibility that the universe, though vast, might be more contained than we think, yet still boundless in a different way. An additional layer to this theory involves the cosmic inflation theory, a critical concept in modern cosmology. This theory proposes that, in the moments following the Big Bang, the universe underwent a period of rapid expansion. It suggests that the universe expanded exponentially faster than the speed of light, setting the stage for the structure we recognize today. The initial inflationary phase led to the formation of galaxies, stars, and the cosmic backdrop we observe in the night sky. This theory not only explains the large-scale homogeneity of the universe, but also introduces the idea that distinct regions of the cosmos could possess different physical laws and constants, each governing their own unique environments. While we can define the boundary of the observable universe by what we can currently detect, the true expanse of the universe remains elusive and tantalizingly beyond our reach. Every new advancement in technology and every new powerful telescope launched into space allows us to extend our observational limits, inching closer to an understanding of the cosmos that continues to evolve. This journey is more than just a scientific pursuit. It invokes a profound sense of awe and wonder at the mysteries still hidden just beyond our current horizon. The vastness of what lies beyond our observable universe stirs deep philosophical questions, sparking the imagination of both scientists and thinkers. One widely debated concept is the notion of an infinite number of universes, collectively known as the multiverse theory. According to this theory, our universe may be just one among potentially countless others, each with its own set of physical laws and constants. Some of these universes could differ radically from ours, while others may share similarities, presenting variations of the cosmos we know. The idea of the multiverse arises from interpretations of quantum mechanics and the theory of inflation. It suggests that different regions of space could have distinct properties, perhaps giving rise to multiple universes. These universes could exist side by side, entirely disconnected from one another, yet still part of a grander, more complex reality. In this view, the fabric of space itself could be a vast expanse, woven with innumerable threads, each representing a different universe with its own unique characteristics. Another mind-expanding idea is that the universe could be embedded in a higher dimensional space. String theory, for example, proposes the existence of additional spatial dimensions beyond the three we experience in daily life. If true, our universe may be confined to a three-dimensional surface within a larger multidimensional space. This opens up a realm of possibilities, suggesting that what we perceive as the known universe might be just one slice of a much larger reality, a slice constrained by the limits of our perception. The existence of these extra dimensions could harbor entirely new physical phenomena, potentially leading to entirely new realms where the laws of nature differ from what we experience. There are also intriguing speculative ideas about the nature of existence itself. Some of these ideas center around concepts like dark matter and dark energy, two mysterious and invisible forces that have been inferred based on their gravitational effects on visible matter. As scientists probe deeper into the cosmos, they encounter realms that remain hidden from direct observation, but whose presence is inferred through their impact on surrounding matter. These unseen forces may represent pathways to dimensions or realities beyond our current ability to detect, hinting at a far richer and more complex universe than we can even imagine. Each of these theories and ideas presents an invitation to explore the vast, mysterious universe around us. They challenge our assumptions and push the boundaries of what we know, keeping our curiosity alive as we venture into the unknown. The uncharted regions of the universe, beyond the reach of current technology and observation, remain an endless source of wonder, mystery, and discovery. Black holes are among the most captivating and enigmatic phenomena in the universe. These objects, with their immense gravitational pull, play a significant role in shaping the cosmos, particularly at the extreme edges of the universe, where galaxies thin out and space itself begins to stretch. Despite appearing as voids in the fabric of space, black holes are anything but empty. They influence their surroundings dramatically, warping the very structure of space-time. Two primary types of black holes are relevant to our discussion: stellar black holes, formed from the collapse of massive stars, and supermassive black holes, which reside at the centers of most galaxies. As galaxies form and evolve, supermassive black holes exert a profound influence on the dynamics of the galaxy. They affect star formation, regulate the movement of galaxies, and even control the orbits of stars around them. These black holes, with their immense mass and gravity, dictate the overall structure of galaxies. Even at the edges of the universe, black holes continue to impact their environment. As they consume surrounding gas and dust, they emit powerful jets of energy and radiation that can illuminate vast areas of space. These jets can reach immense distances, creating spectacular cosmic phenomena and shedding light on the early universe's chaotic and dynamic nature. The study of black holes, particularly those at the outermost regions of the cosmos, offers astronomers valuable insights into the birth and evolution of galaxies and large-scale cosmic structures. In the final analysis, black holes are not just cosmic oddities. They are crucial pieces in the puzzle of understanding how galaxies form and evolve over billions of years. Their impact on surrounding space, the behavior of matter under extreme conditions, and their potential to unlock the mysteries of space-time itself ensures that black holes will remain one of the most fascinating subjects in the study of the universe. The study of black holes, particularly those at the very edge of the universe, propels scientific exploration into some of the most profound and fundamental questions about the nature of gravity, space, and time. These enigmatic cosmic entities, often invisible yet infinitely powerful, act as natural laboratories for testing our understanding of the universe's most mysterious forces. As we observe the behaviors and interactions of black holes with their surrounding environments, each discovery brings us one step closer to unraveling the secrets of the cosmos. These black holes serve as cosmic puzzles, with every new piece of information revealing how deeply interconnected the vast structures of space truly are. Even at the most remote corners of the universe, where light struggles to travel across immense distances, the actions of black holes ripple through space, affecting not only their immediate surroundings, but also shaping the universe on a grander scale. At the same time, the cosmic microwave background, often abbreviated as the CMB, presents a unique glimpse into the very infancy of the universe. This faint, pervasive glow of radiation fills all of space and serves as a critical relic from the universe's earliest moments. It represents the remnant heat from the Big Bang, a cataclysmic event that occurred approximately 13.8 billion years ago, marking the birth of the universe as we know it. The CMB holds an invaluable record of the universe when it was just about 400,000 years old, providing scientists with precious insights into the conditions that prevailed during this extremely early epoch. In the beginning, the universe was an overwhelmingly hot and dense place, where light was unable to travel freely. Instead, it was trapped, constantly bouncing around within the dense plasma of particles. As the universe expanded and cooled, it eventually reached a critical point where atoms could form, allowing light to break free. This moment of transition, from a hot, opaque, and dense soup of particles to a cooler and more transparent state, is what we now observe as the cosmic microwave background. This radiation, which permeates all of space, is not entirely uniform. It carries tiny fluctuations, minute variations that provide a map of the early universe's structure. These fluctuations, though almost imperceptible, are deeply significant. They represent the seeds of future galaxies and large-scale cosmic structures. By studying these subtle differences in the CMB, scientists can piece together a picture of how the universe evolved and where galaxies would eventually form. These tiny variations in matter density in the early universe served as the blueprint for everything we see today in the cosmos. the fluctuations in the CMB are, in essence, echoes of the universe's earliest days, revealing the patterns that would later give rise to the vast cosmic structures we observe. The study of the CMB has been a cornerstone in confirming the Big Bang Theory, reinforcing our understanding of the universe's origins. Moreover, it has allowed scientists to refine fundamental parameters such as the age, composition, and rate of expansion of the universe. The CMB not only provides a snapshot of the past, but it also offers critical clues about the future, helping us understand how the universe continues to evolve. Each new piece of data drawn from this radiation brings us closer to answering some of the most profound questions about the universe's past, present, and future. Furthermore, the cosmic microwave background, CMB, has uncovered a revolutionary discovery. Not only is our universe expanding, but this expansion is actually accelerating. This groundbreaking realization led to the conceptualization of dark energy, a force that remains one of the greatest mysteries in cosmology. The CMB, far from being a mere relic of the past, has become a vital instrument in deciphering the universe's earliest moments, its ongoing evolution, and the cosmic forces that will shape its far-off future. Through the CMB, we are granted an unprecedented glimpse into the very fabric of the cosmos, allowing us to explore not just how our universe began, but how it continues to evolve and how its ultimate fate might unfold. It's a window into the unknown, a tool that helps us better understand our place in this vast, ever-expanding universe. As we look deeper into the cosmos, we encounter countless mysteries that continue to baffle scientists and challenge our understanding of the universe. One of the most intriguing of these enigmas is dark matter. Though invisible, dark matter is thought to comprise roughly 27% of the total mass and energy of the universe. Yet it doesn't emit, absorb, or reflect light, making it incredibly difficult to detect directly. Its presence, however, is inferred from the gravitational effects it has on visible matter, including galaxies and the CMB. Despite decades of research, the true nature of dark matter remains a puzzle. Many theories suggest that dark matter may consist of exotic particles yet to be discovered, a tantalizing possibility that continues to elude us. Equally perplexing is dark energy, a mysterious force that is believed to account for around 73% of the universe's total energy content. Dark energy seems to be responsible for the accelerated expansion of the universe. Since the late 20th century, astronomers have observed that galaxies, far from slowing down, are actually moving away from each other at an increasing speed. This observation suggests the presence of an unseen force, one that is pushing galaxies apart. Yet, despite its dramatic impact on the cosmic scale, we still don't fully understand what dark energy is, how it works, or where it came from. The universe's ultimate fate is at the mercy of the interplay between dark energy and gravity, raising profound questions about whether the universe will continue expanding indefinitely, or if some other force yet to be discovered could reverse its expansion. Another captivating enigma that continues to intrigue scientists is the formation of black holes, particularly the supermassive black holes found at the centers of most galaxies. The origins of these cosmic giants remain largely unknown. How did they grow to be millions or even billions of times more massive than our own sun? Some theories suggest they may have formed from the collapse of massive stars in the early universe, but this explanation doesn't account for the existence of supermassive black holes in galaxies that are much older. This gap in our understanding fuels ongoing research into the complex process of black hole formation and evolution. Finally, we are left to contemplate the nature of the universe itself. How did the universe begin? Does it have an edge, or is it infinite in its vastness? The prevailing theory, the Big Bang, suggests that the universe expanded from an initial singularity, a state of infinite density. However, the question of what came before the Big Bang, or whether our universe is just one among many in a vast multiverse, remains an open one. These questions push the boundaries of our knowledge, urging us to explore ever deeper into the cosmos. In the vast tapestry of the universe, dark matter and dark energy stand out as two of the greatest mysteries of modern cosmology. Together, these unseen entities make up a staggering 95% of the universe's total energy content, yet their true nature remains hidden from our understanding. Dark matter, though invisible, plays a crucial role in shaping the structures we observe in the universe. Without it, galaxies would not hold together, they would simply fly apart due to the gravitational forces exerted by their own stars. This invisible mass provides the gravitational glue that binds galaxies and clusters of galaxies, influencing their formation and evolution. On a much grander scale, dark energy is thought to be responsible for the accelerated expansion of the universe. Since the late 1990s, astronomers have observed distant galaxies receding from us at an ever-increasing speed, a phenomenon that suggests the existence of a force pushing them apart. This force, known as dark energy, constitutes about 70% of the universe's total energy content. Despite its profound influence on the cosmos, the exact mechanics of dark energy remain a mystery. Various theories abound, but none have provided a conclusive explanation. Understanding dark matter and dark energy is crucial not just for understanding the present state of the universe, but also for uncovering the fundamental nature of reality itself. Research into these cosmic puzzles continues, with astronomers and physicists using cutting-edge technology and innovative methodologies to search for answers. By studying cosmic background radiation, observing the movement of distant galaxies, and analyzing the effects of gravitational lensing, scientists are collecting valuable clues that may eventually reveal the true nature of dark matter. As our understanding deepens, these enigmatic forces continue to captivate our imaginations, challenging our perceptions and forcing us to reconsider our place in the universe. The more we learn, the more we realize that there is an almost infinite amount left to discover, keeping us constantly intrigued by the vast mysteries of the cosmos. When we peer into the cosmos, we are not simply observing stars and galaxies. We are tracing the epic story of cosmic evolution. One of the most captivating chapters in this story is the formation of galaxies, particularly those at the edge of the observable universe, billions of light years away. As we look at these distant galaxies, we are looking back in time, often more than 13 billion years, to the earliest moments of the universe's existence. This raises profound questions. How did these galaxies form so early in the universe's history, when the cosmos was far smaller and denser? How did gas and dust coalesce into galaxies in such extreme conditions? One possibility is that these galaxies formed from smaller clumps of matter that merged over time. Another theory suggests that dark matter may have played a pivotal role facilitating rapid galaxy formation in the early universe. But these are only hypotheses. We are still far from a definitive answer. Even more intriguing is the question of what these early galaxies looked like. Were they similar to the galaxies we see today, or did they possess unique characteristics? Observations suggest that these distant galaxies were often very different from their modern counterparts. For example, some of them exhibited extremely high rates of star formation, far outpacing anything we see in galaxies today. Understanding why these distant galaxies were so active could provide crucial insights into the fundamental processes that drive galaxy formation and evolution, offering us a deeper understanding of the universe's earliest chapters. The questions we ask as we peer deeper into the universe are not just about the nature of distant galaxies or the forces that shape the cosmos. They are questions about the very origins of the universe itself. With each discovery, we come closer to unraveling the profound mysteries that lie at the heart of existence. And as we continue to explore the cosmos, one thing becomes clear: the journey of discovery has only just begun. The vast cosmos is an endless source of intrigue, with questions that continue to challenge our understanding of the universe. As we explore the universe's deepest mysteries, we find ourselves grappling with the imprints left by cosmic events that shape and influence everything around us. One of the most significant areas of investigation involves galaxies and the profound impact of their brightest stars and supermassive black holes. The intense radiation emitted by these stellar phenomena doesn't just dissipate into space. It shapes the environments in which these galaxies reside. How did this radiation affect the surrounding space? What role did it play in the creation and evolution of galaxies themselves? These are the types of questions that scientists are striving to answer. By understanding the interactions between these galaxies and their surroundings, we can begin to unlock the secrets of how they evolved and, in turn, how they have contributed to the broader cosmic tapestry. The answers to such questions extend beyond mere curiosity. They are essential for piecing together the entire history of the universe. The story of galaxies at the very edge of the universe is, in essence, a story of the entire cosmos. As we examine galaxies far and wide, we delve into the very heart of the universe's formation. The more we learn, the clearer it becomes that understanding the smallest components, such as stars and black holes, also gives us insights into the broader structures that shape the fabric of everything we know. At the core of this relentless quest for knowledge is the scientific community's unyielding curiosity. The universe is full of unknowns, and understanding it is an endeavor that both fascinates and challenges scientists worldwide. However, uncovering the universe's secrets is no easy task. The methods used to explore these mysteries are multifaceted, blending observation with theory in ways that constantly push the boundaries of human knowledge. One of the primary tools used by astronomers and physicists is advanced telescopes and observatories. These instruments capture light and other forms of radiation emitted by celestial bodies, from the faint glow of distant stars to the powerful bursts from black holes. By analyzing this data, scientists can infer the properties of these cosmic objects. It is through this analysis that astronomers piece together the puzzle of the universe, inferring the characteristics of galaxies, stars, and even dark matter, one of the most elusive substances in the cosmos. In addition to observational techniques, scientific inquiry also relies heavily on experiments conducted here on Earth. Particle accelerators, like the Large Hadron Collider, recreate conditions similar to those present just moments after the Big Bang. These experiments shed light on the fundamental particles and forces that underpin the universe. It is through these groundbreaking experiments that scientists gain a deeper understanding of the building blocks of the cosmos. While conducted on Earth, the implications of these findings stretch far beyond our planet, helping to refine our knowledge of the entire universe. Theoretical models also play a crucial role in the scientific process. These complex computer simulations are instrumental in testing hypotheses about the nature of the universe. Scientists use them to simulate cosmic events such as the formation of galaxies and the behavior of dark energy, an enigmatic force believed to be responsible for the accelerating expansion of the universe. By testing different scenarios, researchers can predict the outcomes of various events and compare them with observational data to see whether their current understanding holds true or needs refinement. This back and forth between theory and observation is a key part of how our understanding of the universe is built and refined. Equally important is the role of collaboration in this ongoing scientific effort. Researchers across various disciplines, whether astrophysics, cosmology, or particle physics, work together, sharing insights and discoveries that help shape the collective understanding of the cosmos. These interdisciplinary partnerships are essential for piecing together the vast, intricate puzzle of the universe, continually broadening the scope of discovery and propelling humanity's knowledge further than ever before. As technology advances and our tools become ever more sophisticated, the boundaries of the unknown shrink. With each new discovery, new questions arise, sparking a continual cycle of exploration and investigation. One particularly intriguing and mysterious phenomenon that challenges our conventional understanding of the universe is the existence of rogue planets, celestial bodies that drift through space without being bound to any star. These planets do not orbit a parent star, and their very existence challenges our traditional views of planetary formation and dynamics. Traditionally, planets were thought to be primarily satellites of stars, held in stable orbits due to gravitational pull. The discovery of rogue planets, however, suggests a much more chaotic and dynamic environment in the cosmos than previously imagined. These free-floating planets might originate from young planetary systems that experience gravitational disruptions, which can result in planets being ejected into interstellar space. As scientists continue to investigate the processes that lead to the formation of rogue planets, they also begin to reconsider how frequently such events might occur. This invites us to think about the possibility that there may be far more planets in the universe than we have yet detected, planets that remain hidden as they drift alone through the void of space. What's even more fascinating is that rogue planets may offer unique conditions for life. Though these planets do not receive light from a star, some scientists theorize that they could possess internal heat. This warmth might come from radioactive decay or the residual energy left over from their formation. If these planets harbor internal sources of energy, it raises exciting questions about the potential for life. Could life in some form arise on a rogue planet? Could the building blocks of life exist without the warmth and light of a sun? These are questions that continue to challenge our preconceived notions about where life can exist in the universe and what forms it might take. As we continue to explore these unknown realms, we find that the universe is not just an endless void, but a dynamic, ever-changing environment, filled with mysteries that continue to challenge and expand our understanding. Every discovery, every breakthrough, opens new doors for further investigation and exploration, reminding us that the universe is far more complex and interconnected than we have yet begun to understand. The pursuit of this knowledge is a journey that will continue for generations to come. The study of rogue planets serves as a powerful reminder of our place in the cosmos. These enigmatic planets, drifting through the vast emptiness of space, far from their stellar companions, stir a deep sense of awe and curiosity. As they wander alone, far from the warmth and light of a sun, they challenge our perception of the universe, revealing just how much remains beyond our own solar system. Rogue planets emphasize the immensity of the cosmos, filled with untold mysteries. Each one serves as a profound symbol of the unknown, urging astronomers and cosmologists to continuously expand and refine our understanding of the universe's intricacies. The very existence of rogue planets invites us to reconsider our understanding of planetary systems, highlighting the sheer unpredictability of space and the potential for countless worlds we have yet to discover. These solitary wanderers may be detached from stars, but they are not without purpose. Each rogue planet offers a glimpse into the mysteries that govern celestial mechanics and planetary formation. Their study underscores that the universe is far more complex than we can imagine, and their discovery fuels a relentless drive to push the boundaries of our knowledge. At the frontier of modern theoretical physics, the concept of dimensions beyond the familiar three has captivated the imaginations of scientists. One of the most compelling theories in this domain is string theory, which proposes that the very building blocks of the universe are not particles, but rather tiny vibrating strings. These strings are thought to require additional dimensions beyond the ones we perceive with our senses in order to vibrate and oscillate in specific ways. String theory suggests that there could be as many as 10 or even 11 dimensions, with some of these dimensions being compacted and hidden from view. These extra dimensions are difficult, if not impossible, to detect with the technology currently at our disposal. Alongside string theory, another intriguing concept has emerged: the multiverse theory. This idea suggests that our universe is not a solitary entity, but rather one among an infinite number of universes, each with its own set of physical laws and properties. Some versions of this theory suggest that these universes exist within a higher dimensional space, and interactions between them could manifest as phenomena we observe in our own universe. This concept hints at the existence of far more intricate and sophisticated structures than we can currently perceive, challenging the limits of our scientific imagination and pushing us to reconsider our place in the cosmic order. Physicist Kip Thorne and other prominent thinkers have expanded on these ideas, speculating about the potential existence of warped dimensions, in which shortcuts through space-time might connect distant parts of the universe, or even entirely different universes. Such theoretical connections could offer possibilities for faster-than-light travel, instant communication, or perhaps even new forms of understanding about the very nature of reality itself. While these ideas are still speculative, they have sparked boundless creativity and imagination, opening the door to profound questions about space, time, and existence. As research continues, scientists are tirelessly searching for ways to detect or even visualize these hidden dimensions. However, their existence remains theoretical, and much work remains to be done before these hypotheses can be tested with any certainty. The discovery of extra dimensions, if proven true, would upend everything we know about space-time and the fundamental nature of reality. It would provide us with a glimpse into a universe far richer, more complex, and more mysterious than we can even begin to comprehend. For many, this idea is more than a scientific hypothesis. It is a gateway to exciting possibilities, a call to challenge the very fabric of our understanding. Parallel universes, an extension of the multiverse concept, offer yet another layer of mystery and fascination. This idea proposes that not only does our universe exist, but it is one of many, perhaps an infinite number of alternate realities, each existing alongside our own, but following its own set of laws and conditions. This perspective radically reshapes how we think about existence, especially when we approach the very edge of our observable universe. Rather than encountering a firm boundary or an empty void at the edge of the cosmos, the concept of parallel universes suggests that beyond our own reality lies an infinite landscape of possibilities. This boundary may not be the end at all, but rather the beginning of something far more expansive, where other versions of reality exist in parallel. If parallel universes are indeed real, they may host entirely different physical laws, forms of matter, and even alternative versions of time itself. The very idea challenges our assumptions about the uniqueness of our universe, forcing us to reconsider what it means for something to be real. This concept has far-reaching implications for our understanding of identity and consciousness. If there are infinite versions of ourselves, living out different choices and experiences in countless universes, we are prompted to reconsider the nature of individuality. Could our experiences, which we interpret as singular and unique, simply be one thread in a vast, interconnected tapestry of lives? This philosophical question invites profound introspection about the nature of self and the limits of perception. Exploring parallel universes invites a sense of wonder and humility. As we face the possibility that we are just one of many threads in the multiverse, we begin to appreciate the vastness of existence in a new way. This perspective challenges us to look beyond our narrow view of reality, encouraging a deeper understanding of the interconnectedness of all things. In this context, the universe, rather than being a solitary expanse, becomes a vast, intricate network of possibilities, each more extraordinary than the last. In contemplating the multiverse, we not only reframe our understanding of the cosmos, but also come to terms with our place within it. We are not isolated beings in an empty universe. We are part of an expansive, dynamic reality that stretches far beyond the limits of our comprehension. The multiverse invites us to see ourselves not as solitary entities, but as interconnected parts of a much grander cosmic story. The multiverse theory offers a compelling explanation for some of the universe's most puzzling features. For instance, the fine-tuning of physical constants, such as the strength of gravity or the charge of an electron, seems to allow for life as we know it. The multiverse theory posits that, given the vast number of universes, it is not surprising that one of them would possess the precise conditions necessary for life. This idea helps to address one of the great mysteries of science. Why do the physical constants of our universe seem so perfectly tailored to support life? However, despite its appeal, the multiverse theory remains highly controversial. Critics argue that it lacks empirical support and cannot be tested using traditional scientific methods, which rely on observation and experimentation. Without concrete evidence to support the existence of other universes, the multiverse remains more of a philosophical concept than a scientific hypothesis. This uncertainty has led to skepticism among those who prefer theories grounded in observable, testable phenomena. Ultimately, the idea of parallel universes, along with all its philosophical and scientific implications, serves as a reminder of the limits of our current understanding. Yet, it also offers a tantalizing glimpse into the possibilities that lie beyond. As we continue to explore the deepest reaches of space and ponder the nature of reality itself, we are confronted with the overwhelming vastness of the cosmos and the infinite potential for discovery. It is a humbling and exhilarating reminder that we are only beginning to scratch the surface of the mysteries that lie hidden just beyond our reach. Furthermore, some critics of the multiverse theory raise deep philosophical questions about the very nature of reality itself. If every possible version of events exists somewhere in an infinite web of universes, this could suggest a reality where nothing is truly unique or meaningful. Such a perspective, often linked to nihilism, calls into question the significance of our existence. It proposes that in a cosmic sea of infinite possibilities, every event, every choice, every life may be just one of countless variations. This line of thought invites profound contemplation on the implications of reality. What does it mean if everything that could ever happen, in some form, exists elsewhere? If nothing is truly singular, how do we assign value or purpose to our experiences? This brings us to a deeper examination of what it truly means to observe and experience our own universe. In a world where the fabric of reality could be mirrored across infinite dimensions, can we still assert that our lives hold intrinsic worth? These perspectives demand that we reconsider our place in the grand cosmos. Are we just a fleeting blip in an unending cosmic cycle, or do we have the power to shape meaning in a universe that might, in its most fundamental sense, be indifferent to our existence? This philosophical dilemma is at the heart of the ongoing debate surrounding the multiverse theory. It sits at the crossroads of science, philosophy, and our collective understanding of existence. The theory opens a gateway to fascinating, mind-bending questions about the very nature of the cosmos. What does it mean for the fundamental laws of physics when reality can take on infinite forms? What are the true limits of possibility? And how far do the boundaries of our universe stretch? As our technologies advance and our scientific methodologies evolve, we continue to seek evidence that could either confirm or challenge the theory. Perhaps, in time, we will find new insights that could reshape our understanding of everything we know, or even lead us to an entirely different conception of reality. As we turn our focus to the concept of the edge of the universe, we find ourselves standing on the precipice of profound mysteries and groundbreaking discoveries. The universe, as far as our instruments can observe, is expanding outward at an ever-increasing rate. This expansion suggests that the universe may have a boundary, a limit, and edge that we are only beginning to understand. However, comprehending what lies beyond this boundary is a perplexing and elusive challenge. The very nature of space itself becomes a question. Does the universe truly have an edge, or does it simply continue forever in all directions? If such a boundary exists, it could hold the key to understanding some of the most fundamental laws of physics. It may offer insights into the origins of the universe, providing clues about how cosmic structures first emerged and evolved. By studying the universe's edge, we might uncover critical information about the distribution of galaxies, the cosmic microwave background radiation, and other remnants from the Big Bang, traces that could confirm or refute existing theories of cosmic evolution. This could allow us to determine whether the universe adheres to the established rules of general relativity, or whether quantum mechanics may play a more prominent role in the very structure of space-time. The edge of the universe could also offer an answer to one of the most profound questions of all. Is the universe finite or infinite? This is no mere academic question. It has far-reaching implications for how we understand the nature of existence. If the universe is infinite, it suggests that reality itself might be boundless, with no true limits. On the other hand, if it is finite, it suggests a universe with a beginning and an end, a timeline with defined parameters that we might one day explore. Additionally, investigating this boundary could yield critical insights into two of the most mysterious and elusive components of the universe: dark matter and dark energy. These forces make up the vast majority of the universe's mass and energy content, yet they remain largely invisible and undetectable by conventional means. They exert influence over the cosmos, shaping the expansion of the universe and the movement of galaxies. Understanding how these substances behave at the edge of the universe could reveal much about their nature and their role in the cosmic framework. Perhaps, through these explorations, we might even discover new forces of nature, forces that we have yet to imagine, waiting at the limits of our understanding. The edge of the universe thus represents a tantalizing cosmic puzzle, one that challenges us to rethink our place in the cosmos and refine our understanding of the laws of physics. It beckons us toward deeper inquiry, urging us to push the boundaries of knowledge and to venture into the unknown. As we turn our telescopes toward the heavens and peer ever deeper into the void, we are reminded that the pursuit of cosmic truths is an ongoing journey, one that will likely reveal far more than we ever imagined, and whose answers may forever alter our view of reality. In parallel, string theory offers a compelling and revolutionary framework in theoretical physics. It proposes a radically different view of the universe's fundamental components. Instead of thinking of particles such as electrons and quarks as small, point-like objects, string theory suggests that they are, in fact, one-dimensional strings that vibrate at different frequencies. This tiny yet profound shift in perspective transforms our understanding of matter and energy, offering new possibilities for how the universe works at its most basic level. One of the most captivating aspects of string theory is its potential to explain the existence of multiple dimensions beyond the familiar three of space: length, width, and height that we experience in our everyday lives. According to string theory, there could be as many as 11 dimensions when we account for additional spatial dimensions that are compactified or curled up so small that they are imperceptible to our senses. These extra dimensions may be hidden from view, but their presence could have far-reaching implications for our understanding of reality. This concept radically expands our view of what is possible in the universe. These hidden dimensions could host entirely different structures, forces, and even parallel realities that lie beyond our current understanding. Some theories propose that these unseen dimensions may influence the formation of galaxies, or that they might alter the way gravity operates on large cosmic scales. This opens up the possibility that what we perceive as our universe might only be a tiny fragment of a much larger multidimensional landscape, one where different strings and their various vibrations give rise to all the particles and forces we observe in the visible universe. In this multidimensional landscape, the possibilities for what could exist are endless, and the implications of string theory could fundamentally reshape our understanding of the cosmos. It is a theory that continues to evolve, one that invites us to look beyond the limitations of our perception and explore a reality that may be far more intricate, complex, and awe-inspiring than we ever imagined. Moreover, this framework opens the door to the extraordinary concept of multiple universes, often referred to as the multiverse. Each universe could potentially operate under different sets of physical laws and properties, influenced by the unique vibrations of strings within their distinct dimensional configurations. Though string theory remains largely theoretical, still awaiting empirical confirmation, its far-reaching implications compel us to expand our thinking about the nature of reality itself. It pushes the boundaries of what we know, urging us to contemplate what lies beyond the cosmos we are familiar with. The idea of higher dimensions and parallel universes evokes a profound sense of wonder and curiosity about the sheer vastness and complexity of the unknown that stretches beyond our universe. As we journey toward the enigmatic edge of our cosmic home, numerous groundbreaking advancements in technology are essential for deepening our exploration. One of the most crucial developments in recent years has been the creation of advanced telescopes. Instruments like the James Webb Space Telescope have revolutionized our ability to peer into the farthest reaches of the universe. These telescopes are equipped with incredibly powerful mirrors and highly sensitive detectors that allow us to capture the faint light emitted by distant galaxies and stars that formed billions of years ago. This remarkable capability doesn't just enhance our understanding of the universe's history. It also reveals the chemical makeup of celestial objects that reside at unimaginable distances from us. But telescopes aren't the only instruments transforming our understanding of the cosmos. In addition to advancements in optical technology, significant strides have been made in the realm of radio astronomy, which opens entirely new frontiers. Powerful radio telescopes, such as the ones employed in large-scale projects like the Square Kilometre Array, allow us to detect the radio waves emitted by various celestial phenomena. These radio waves offer a distinct perspective on the universe, shedding light on star formation, black holes, and cosmic background radiation. Radio astronomy provides us with access to parts of the universe that are too faint or obscured for optical telescopes to observe. By capturing these elusive waves, we gain insights into regions of space that were once invisible to our eyes, revealing the complex processes that govern the formation and evolution of celestial objects. Meanwhile, digital technology has reshaped our ability to handle vast amounts of astronomical data. With the rise of artificial intelligence and machine learning, scientists can now process data from telescopes more efficiently and accurately than ever before. These technological innovations allow for rapid identification of celestial objects and events, helping scientists predict the behavior of complex cosmic systems. By turning raw data into meaningful insights, these advancements propel us forward in understanding the intricate structure and evolution of the universe. As space exploration missions continue to push the boundaries of what is possible, spacecraft technology plays a vital role in making these missions feasible. Innovations in propulsion systems, such as ion engines, are poised to revolutionize space travel, offering more efficient ways to traverse the vast distances within our solar system and beyond. These technological leaps are not just about sending robotic probes into deep space. They are paving the way for human exploration of distant worlds. Whether we are talking about crewed missions to Mars or robotic spacecraft sent to the farthest reaches of the galaxy, these advancements are critical to ensuring the safety and success of future space exploration endeavors. Together, these breakthroughs in telescopes, radio astronomy, data analysis, and spacecraft design are laying the groundwork for humanity's ability to explore the profound mysteries that await us at the very edges of the universe. Telescopes, in particular, stand out as the quintessential tools for unlocking the secrets of the cosmos. These remarkable instruments allow us to look deep into space, gathering light that has traveled across vast stretches of time. When a telescope is directed at a distant celestial body, it collects light emitted or reflected by that object. This light carries invaluable information about the composition, motion, and distance of the object, offering a window into the universe's farthest reaches. There are many different types of telescopes, each tailored to capture light in its own way. Optical telescopes, for example, use mirrors or lenses to collect visible light. Reflecting telescopes rely on mirrors to focus this light, while refracting telescopes use lenses for the same purpose. These telescopes are capable of capturing faint light from faraway stars and galaxies, allowing astronomers to observe phenomena that are invisible to the naked eye. The larger the mirror or lens, the more light the telescope can collect, enhancing its ability to observe objects that lie at even greater distances. But optical telescopes are just one piece of the puzzle. Radio telescopes, which detect radio waves, and infrared telescopes, which capture infrared radiation, also provide unique perspectives on the universe. Each type of telescope is designed to explore different regions of the electromagnetic spectrum. For instance, while optical telescopes are limited to the visible light range, radio telescopes can reveal critical details about cosmic elements such as gas clouds and radiation. These discoveries are vital for understanding the formation processes of stars, galaxies, and other celestial phenomena. Many of today's most advanced telescopes are positioned in remote locations or even launched into space. By placing telescopes above Earth's atmosphere, such as the Hubble Space Telescope, astronomers can bypass the distortions caused by atmospheric interference, resulting in much clearer and sharper images. These space-based instruments have allowed scientists to delve deeper into the mysteries of galaxies that formed billions of years ago, and to gain a better understanding of the fundamental mechanisms that govern the universe. Another groundbreaking advancement in cosmic exploration comes in the form of gravitational wave detection. This technology provides a new way to study the universe, offering unprecedented insights into the most violent and energetic events in space. Gravitational waves, first predicted by Albert Einstein in his theory of general relativity, are ripples in spacetime that are caused by catastrophic events like black hole mergers and neutron star collisions. By detecting and analyzing these waves, scientists are not only learning more about these specific cosmic events, but are also uncovering fundamental truths about the nature of the universe itself. Gravitational wave detection has the unique ability to redefine our understanding of cosmic distances. Traditional methods of measuring distances across the universe often rely on light signals, but gravitational waves can travel vast distances without being hindered by obstacles like gas clouds or dust. This means that gravitational wave observatories can reach regions of space that might otherwise be hidden from view. As a result, they provide a clearer picture of the universe's structure and the complex dynamics that govern its evolution. Moreover, studying the properties of gravitational waves enables us to explore extreme states of matter. For example, when two neutron stars collide, they create conditions that are simply impossible to replicate on Earth. The waves produced during such violent collisions carry crucial information about the matter in these extreme environments. By decoding these waves, scientists can refine their understanding of physics, gaining deeper insights into the forces and particles that shape our universe. In this way, gravitational wave research is pushing the frontiers of science, allowing us to glimpse the universe in ways that were once unimaginable. Together, these advances, telescopes, radio waves, artificial intelligence, spacecraft propulsion, and gravitational wave detection form the foundation for a new era of cosmic exploration. They are not just tools for understanding the universe as it is today, but instruments that help us imagine what lies ahead, far beyond the limits of our current knowledge. The more we learn, the more we realize how much there is still to discover. Each new breakthrough brings us one step closer to unraveling the mysteries of the cosmos, offering a glimpse into the incredible complexity of the universe and possibly the multiverse that lies just beyond our reach. Gravitational wave detection stands as one of the most groundbreaking advancements in modern science, offering profound insights into some of the most enduring and fundamental questions about the universe. For centuries, humanity has pondered the nature of existence itself, the very fabric of space and time, and whether there are regions of the cosmos beyond our observable universe. In an attempt to answer these questions, scientists have turned to gravitational waves, ripples in space-time that carry information from the furthest reaches of the universe, providing a unique window into phenomena that were once invisible. By studying these cosmic ripples, we are not just pushing the boundaries of scientific knowledge, we are igniting a sense of awe and wonder about the intricate tapestry of reality. With each new detection, we take another step toward unraveling the deeper story of the universe, gaining glimpses into its mysterious birth and structure. One of the most profound inquiries that gravitational waves help address is what happened during the earliest moments after the Big Bang, a time so distant that traditional methods of observation cannot reach it. The exploration of these questions through the lens of gravitational waves is unlocking new realms of understanding and revealing the vastness of the cosmos in ways we could never have imagined. As the quest for cosmic knowledge progresses, artificial intelligence, AI, has become an indispensable tool in helping us analyze the ever-expanding data we collect. The days of astronomers manually sifting through vast amounts of observational data, a painstaking and slow process, are behind us. AI, equipped with powerful machine learning algorithms, now allows us to process and interpret data at speeds and scales previously thought unattainable. This leap forward has revolutionized how we study the universe. AI algorithms are particularly transformative in their ability to identify patterns, detect anomalies, and even make predictions about cosmic events. Unlike traditional methods that relied on human researchers, these advanced systems can sift through enormous datasets in a fraction of the time, identifying subtle signals and phenomena that might otherwise go unnoticed. The potential applications of AI in cosmology are vast, but one of the most compelling is its role in analyzing the incredible volume of images produced by telescopes like the Hubble Space Telescope. These telescopes generate millions of images, each capturing a snapshot of the universe's wonders, from distant galaxies to the formation of stars. Through the power of AI, researchers can automate the detection of specific features in these images, such as the birth of new galaxies or the discovery of exoplanets in far-off star systems. This automation accelerates the analysis process, enhances accuracy, and allows us to explore the cosmos in ways that were once unimaginable. AI can recognize minute details and patterns that even the most experienced astronomers might overlook, making it an invaluable tool in our quest for knowledge. Furthermore, AI plays a crucial role in organizing and interpreting data from large astronomical surveys, such as the Sloan Digital Sky Survey or the Vera C. Rubin Observatory's Legacy Survey of Space and Time. These surveys produce massive databases filled with detailed information about stars, galaxies, and other celestial bodies. AI helps categorize this data, prioritizing which objects should be studied further based on their potential significance. By focusing on the most promising candidates, researchers can make more efficient use of their time and resources, advancing our understanding of the universe at a rapid pace. One of the most exciting potential discoveries that could arise from this data is the detection of extraterrestrial intelligence. If we were to receive a signal from an intelligent civilization in a distant part of the galaxy, the implications would be nothing short of revolutionary. Such a discovery would not only validate the long-held belief that we are not alone in the cosmos, but also raise profound questions about the nature of that life. Are these beings similar to us? Or do they exist in forms entirely beyond our comprehension? What knowledge or wisdom might they share with us? And what intentions might they have? The confirmation of extraterrestrial signals would open up new frontiers of scientific inquiry, sparking a wave of studies in fields such as astrobiology, astrophysics, and exoplanet research. It would compel us to rethink our theories on the formation of life, prompting fresh investigations into the conditions under which intelligent beings could arise. Beyond the scientific realm, the discovery of extraterrestrial intelligence would have a deep cultural impact. It would force humanity to reconsider its place in the universe, challenging our traditional notions of identity, existence, and our connection to other life forms. This realization could spark a sense of unity among humans, as we would no longer view ourselves as isolated beings, but as part of a greater cosmic community. The knowledge that we are not alone could foster greater cooperation and collaboration among nations, as the shared knowledge of other civilizations would transcend borders and divisions. Such a discovery could inspire peace and unity, challenging the concept of national boundaries and encouraging a collective sense of responsibility toward our planet and each other. But along with these exciting prospects come complex ethical questions. How should we respond to intelligent beings from another world? Should we share our technological advancements with them or withhold certain information for our own protection? These questions underscore the importance of careful planning and collaboration, not just within the scientific community, but across all aspects of society. The discovery of extraterrestrial intelligence would require a global effort to navigate the social, political, and ethical challenges it presents, fundamentally altering humanity's trajectory in the process. In parallel with these advancements, the study of cosmic background radiation, often referred to as the afterglow of the Big Bang, provides another fascinating lens through which we can understand the early universe. This faint, nearly uniform glow, detectable in all directions, is the residual heat left over from the universe's infancy, when it was hot and dense. As the universe expanded and cooled, this energy was released, and we now observe it as cosmic microwave background radiation. The patterns in this radiation reveal critical information about the conditions that existed just 380,000 years after the Big Bang, offering a snapshot of the universe's early structure. Tiny fluctuations in temperature and density within the cosmic background radiation point to variations in matter distribution, which helped shape the formation of galaxies. By studying these fluctuations, scientists can better understand the rate at which the universe is expanding and gain insights into the forces that governed its early evolution. This radiation serves as a cosmic map, helping to illuminate the universe's structure and evolution over time. By analyzing these patterns, researchers can estimate the age of the universe itself, which is currently thought to be around 13.8 billion years. Understanding the cosmic background radiation allows scientists to peer deeper into the universe's history, providing clues that will shape our understanding of the cosmos for generations to come. The study of cosmic background radiation is far more than just a technical endeavor. It holds profound implications for our understanding of the universe's most enigmatic elements, such as dark matter and dark energy. This radiation, a remnant of the Big Bang, offers a unique glimpse into the evolution of the cosmos, allowing scientists to piece together clues about the forces that shape the universe, even the unseen ones. As this radiation spread and evolved over billions of years, it carried with it the faintest echoes of the universe's infancy. These echoes do not merely document the history of the universe, they also hold the key to understanding the fundamental laws governing its ongoing evolution and ultimate fate. Through ongoing research and technological advances, cosmic background radiation remains an invaluable tool in unlocking the hidden chapters of our universe's story, both past and future. As we peer deeper into the cosmos, we occasionally detect signals that leave us both amazed and puzzled. These anomalous signals, often originating from the distant reaches of space, can arise from a variety of mysterious sources. One of the most captivating possibilities involves the activity of distant galaxies, especially those hosting supermassive black holes. As matter is drawn toward these cosmic giants, it spirals inward, releasing staggering amounts of energy in the form of radio waves, X-rays, and gamma rays. These emissions travel vast distances across the universe, eventually reaching our telescopes and sparking intense curiosity. Another intriguing source of these enigmatic signals comes from the cosmic phenomena surrounding the birth and death of stars. For example, when a star undergoes a violent explosion called a supernova, it releases a torrent of energy and radiation, sometimes producing remnants that emit strange signals. Among these remnants are pulsars, rapidly spinning neutron stars that emit bursts of radio waves in a rhythmic pattern. This steady beat of radio waves might appear to convey structured information, though it is simply the result of the pulsar's rapid rotation. Moreover, we cannot overlook the influence of cosmic microwave background, CMB radiation. Though this faint glow is an ancient echo of the Big Bang, it continues to fill every corner of the universe. Despite being billions of years old, subtle variations within the CMB can sometimes lead to the detection of unexpected signals, hinting at processes or materials that elude our current understanding. These signals from the past serve as a time capsule, occasionally challenging our existing theories and offering new paths for exploration. As our ability to explore the universe increases, so too does our challenge in distinguishing between natural cosmic phenomena and signals created by human technology. Satellites, space stations, and other artificial technologies orbiting Earth can produce their own emissions that may resemble those of distant cosmic events. The task of differentiating these man-made signals from the natural ones becomes increasingly complex. The exciting pursuit of understanding the universe's many voices is tempered by the intricacies of interpreting each signal. Every anomaly detected is a puzzle waiting to be unraveled, a clue toward a greater understanding of the cosmos. The quest to comprehend the universe's edge has captivated humanity for millennia. Our journey began long before we had the sophisticated tools of modern astronomy, with ancient observers of the night sky laying the groundwork for the field we know today. These early astronomers noticed recurring patterns in the motion of stars and planets, which hinted at a grander, more organized structure within the cosmos. Their observations formed the bedrock upon which subsequent models were built, including the Earth-centered model of the universe proposed by Claudius Ptolemy. This geocentric view dominated Western thought for centuries. As technology advanced, so too did our instruments and our understanding. The invention of the telescope in the early 17th century marked a monumental leap in our ability to explore the heavens. Galileo Galilei, with this revolutionary new tool, made groundbreaking discoveries. Most notably, he observed the moons of Jupiter and the phases of Venus. These observations provided strong evidence against the long-held geocentric view and suggested that the cosmos was far more complex than previously imagined. The universe, it seemed, was not a closed system centered on Earth, but an ever-expanding realm filled with infinite possibilities. The idea of a fixed edge to the universe became increasingly obsolete. The 20th century saw another paradigm shift, thanks to the pioneering work of Edwin Hubble. Hubble's observations of distant galaxies revealed that they were all moving away from each other, leading to the groundbreaking conclusion that the universe itself is expanding. This discovery gave rise to the Big Bang theory, reshaping our understanding of the universe's origins. Instead of viewing the universe's edge as a solid boundary, cosmologists began to think of it in terms of the observable universe, the region of space we can detect based on the light that has reached us since the beginning of time. Today, the knowledge we've accumulated through centuries of observation continues to inform our exploration of the cosmos. Technological advancements allow us to measure and study the cosmic microwave background radiation, offering us glimpses of the universe in its earliest moments. These findings encourage us to reconsider what we mean by the edge of the universe. Is there a definitive boundary? Or are we simply encountering an ever-expanding horizon that will forever elude our grasp? Our understanding of the universe is constantly evolving. Early astronomers, such as those from ancient Babylon, Egypt, and Greece, were the pioneers who began to unravel the mysteries of the night sky. Thousands of years ago, these celestial observers meticulously tracked the movements of stars and planets, developing the first calendars and navigational systems. Their curiosity and insight led to significant cultural and religious developments, and they laid the foundation for the modern study of the cosmos. The Greeks, in particular, made monumental strides in celestial knowledge. Figures like Thales and Pythagoras theorized about the structure of the universe and proposed models that placed Earth at its center. While their geocentric models would later be proven incorrect, their observations sparked important discussions about planetary motion and the overall structure of the cosmos. These early speculations, though primitive by today's standards, ignited a thirst for knowledge that would span centuries and give birth to revolutionary ideas, especially during the Renaissance. As we continue to explore the vast, uncharted reaches of space, we build upon the legacy of these ancient pioneers, constantly refining our understanding of the universe. What once seemed like a collection of mysterious dots in the night sky is now revealed to be a dynamic and ever-expanding universe, filled with phenomena that challenge the limits of our imagination. The search for answers is an ongoing journey, and as we stand at the frontier of discovery, one thing is certain: the universe's secrets are far from fully revealed, and the questions will continue to drive our exploration for generations to come. Moreover, the work of ancient astronomers was instrumental in shaping the foundation of the scientific method. They were the first to emphasize the importance of observation and systematic recording, two crucial elements that continue to be at the heart of modern scientific inquiry. By meticulously documenting their findings and drawing conclusions from what they observed, they encouraged future generations to approach the stars with a critical and methodical eye. This shift in methodology was transformative, laying the groundwork for all subsequent advancements in science and technology. It's no exaggeration to say that the techniques these early astronomers developed remain fundamental today. As we continue to explore the universe with increasingly sophisticated tools and technologies, their contributions resonate across millennia. Their work reminds us of humanity's deep-rooted fascination with the cosmos. A fascination that not only inspired the scientific discoveries of later eras, but also fueled our intrinsic desire to understand the nature of our existence in this vast and mysterious universe. By appreciating the efforts of these early stargazers, we recognize that the age-old quest for knowledge has not only shaped the trajectory of modern scientific endeavors, but also illuminated the path for future cosmic explorations. The way we interpret the universe has evolved profoundly over time, influenced by shifting cultural, religious, and scientific perspectives. In ancient civilizations, the cosmos was often seen through a mythological lens. The stars and planets were frequently personified as gods or divine entities, offering explanations for the natural phenomena that shaped human existence. For example, the Babylonians were among the first to chart the night sky, assigning various deities to celestial bodies. Similarly, the ancient Greeks wove elaborate tales about constellations, filling the heavens with stories of heroes and mythical creatures that danced among the stars. As we move into the Middle Ages, cosmological views were largely shaped by religious doctrine. During this period, the Earth was considered the center of the universe, reflecting the belief that humanity occupied a special, central position in creation. This geocentric model, famously championed by thinkers like Aristotle and Ptolemy, painted a picture of the universe as a realm dominated by divine order and human importance. It wasn't until the Renaissance, however, that a paradigm shift began to take place. The work of astronomers like Copernicus and Galileo led to the emergence of the heliocentric model, which proposed that the sun, not the Earth, was at the center of our solar system. This groundbreaking idea not only sparked further scientific inquiry, but also ignited philosophical debates about humanity's place in the cosmos. The Enlightenment further accelerated these shifts as observation and reason began to take precedence over religious dogma. It was during this period that scientists like Isaac Newton formulated the laws of motion and universal gravitation, presenting a vision of the universe governed by predictable physical laws. The Enlightenment was a turning point, marking the transition from a mystical understanding of the cosmos to one that emphasized rationality and empirical evidence. With the advent of telescopes and the development of advanced mathematical methods, scientists began to uncover new celestial bodies, expanding our understanding of the universe and its intricate workings. In the modern era, our understanding of the cosmos has continued to evolve at a breathtaking pace. Technological advancements such as space telescopes and other sophisticated observational instruments have allowed us to peer deeper into the universe than ever before. What we've discovered is both humbling and awe-inspiring. The universe is far larger, more complex, and more mysterious than we could have imagined. Concepts like the Big Bang and dark matter challenge earlier interpretations of the cosmos, stretching the boundaries of human knowledge to previously unimaginable limits. Today, we find ourselves acknowledging that we are but a small part of an ever-expanding universe, one that prompts profound reflections on our place within it and our connection to the vast expanse that surrounds us. This ongoing journey reflects a profound shift in the way humanity views the universe. From ancient mythologies that explain the stars through the lens of gods and legends, we now approach the cosmos with curiosity, exploration, and an unyielding desire to understand the forces that govern its existence. Throughout history, key discoveries have radically altered our understanding of the universe, revealing its complexities, wonders, and unimaginable scale. One of the earliest breakthroughs in this journey came from the 16th century work of Nicholas Copernicus. He proposed a revolutionary idea, that the Earth revolves around the sun rather than the other way around. This heliocentric model not only challenged the long-held geocentric beliefs of the time, but also set the stage for further exploration of our solar system and beyond. A few centuries later, Sir Isaac Newton made another monumental leap in our understanding of the universe. In the 17th century, his laws of motion and universal gravitation provided a comprehensive framework for understanding how celestial bodies interact. Newton's insights not only helped to explain the orbits of planets and the mechanics of the solar system, but also laid the foundations for classical mechanics, forever changing the field of physics and transforming the way we perceive motion in the cosmos. In the 19th century, the field of spectroscopy opened up new possibilities for astronomers. By studying the light emitted by stars and other celestial objects, scientists could analyze their chemical composition and physical properties. This breakthrough significantly expanded our understanding of the nature of stars and their behavior. By analyzing the light from distant galaxies, astronomers realized that the universe was far larger than anyone had previously imagined. The 20th century ushered in some of the most groundbreaking discoveries in the history of astronomy. One of the most important was the discovery of cosmic microwave background radiation, which provided critical evidence for the Big Bang theory. This discovery offered a glimpse into the earliest moments of the universe, confirming that it had been expanding ever since its creation. Additionally, the observation of distant supernovae in the late 20th century revealed that the universe is not only expanding, but doing so at an accelerating rate. This unexpected revelation led to the concept of dark energy, a mysterious and still largely unexplained force that continues to baffle scientists and challenges our understanding of the cosmos in profound ways. As we continue to explore the vastness of the universe, questions about its edges and its ultimate fate continue to fascinate and intrigue. The more we learn, the more we realize how little we truly know, and the more we are compelled to delve deeper into the mysteries that lie beyond the stars. Cosmological models have undergone a dramatic evolution, reflecting not only advancements in scientific understanding, but also the shift in humanity's perspective on its place in the cosmos. Historically, our conception of the universe was deeply tied to cultural and philosophical beliefs, often suggesting a finite and flat space confined by a celestial dome. In ancient times, the universe was thought to be a limited expanse, bounded by an invisible edge, with celestial bodies moving in a fixed and predictable manner. This view held sway for centuries, shaped by the cosmologies of various ancient civilizations, from the Greeks to the Babylonians, who envisioned a cosmos defined by a solid, structured boundary. However, the dawn of modern science in the 16th and 17th centuries ushered in a profound shift. The advent of telescopes allowed astronomers to peer deeper into space, leading to an expansion of our understanding. By the early 20th century, the development of the Big Bang theory radically altered our view of the universe. This groundbreaking theory proposed that the universe has been expanding ever since its inception, an event that occurred approximately 13.8 billion years ago. Unlike the ancient notion of a finite space, the Big Bang introduced the concept of an ever-expanding cosmos, where the universe's edge was not a physical boundary, but rather a point in time and space from which everything originated. The Big Bang theory brought with it the realization that the universe is not static, but dynamically expanding, and this expansion continues to this day. Galaxies move away from one another, but the universe doesn't have an edge in the traditional sense. Instead, there are regions beyond our detection, places where light hasn't yet reached us, meaning there are areas of space that remain beyond our current observational capacity. This led to the idea that the universe may be infinite with no actual physical boundary. Later, the concept of cosmic inflation, proposed by physicist Alan Guth in the 1980s, added even more complexity to our understanding. This theory suggested that moments after the Big Bang, the universe underwent a period of rapid expansion. So rapid, in fact, that within a fraction of a second, space grew exponentially. This rapid inflation not only helped explain the uniformity of the cosmic microwave background radiation, which is the afterglow of the Big Bang, but also clarified why the universe appears flat on large scales. Essentially, cosmic inflation proposed that the observable universe is just a small fraction of what may be an ever-growing, eternally shifting cosmos. Today, these theories continue to evolve with new research, particularly in the realms of quantum physics and the mysterious forces of dark energy and dark matter. Dark energy, an enigmatic force driving the accelerated expansion of the universe, and dark matter, a substance responsible for holding galaxies together, continue to be crucial components in refining our models. With each new discovery, our grasp of the universe's structure grows deeper, shedding light on the very mechanisms that drive cosmic expansion and evolution. Yet the more we learn, the more we realize how much remains unexplained. In recent years, the idea of a multiverse has gained traction, suggesting that our universe may not be the only one. One of the most fascinating ways to explore this idea is through the concept of bubble universes. Imagine our universe as a single bubble floating within a vast sea of other bubbles, each representing a distinct universe. These universes could be governed by different physical laws, potentially existing in entirely different forms and conditions. This multiverse hypothesis challenges the classical view of the universe as a singular, isolated reality. Instead, it proposes that boundaries, if they exist at all, are more abstract than we once imagined. With bubble universes, the question of boundaries takes on new meaning. In the classical sense, the universe was a finite space with a clear beginning and edge. But now, in this new model, the universe is one among potentially countless others. Each bubble universe may have its own set of rules, sizes, and histories, some of which may support life forms completely different from anything we can comprehend. This radically reshapes our perception of existence, pushing us to reconsider what we know about life, evolution, and the very fabric of reality. The idea that the universe might be just one part of a larger cosmic landscape introduces profound implications for our understanding of the cosmos. The existence of multiple universes implies that the universe we observe could merely be a small slice of an infinitely larger and more complex whole. These other universes could operate under entirely different conditions, with varying laws of physics, giving rise to diverse forms of matter, and perhaps even life that differ radically from anything we can imagine. As we expand our cosmic horizons, the very notion of a boundary becomes increasingly elusive. Rather than thinking of the universe as a contained space with a definitive edge, we are now forced to consider a boundless, ever-expanding cosmos. Each new discovery, from the study of dark energy to the multiverse theory, reshapes our understanding of space, time, and existence itself. The Big Bang Theory remains foundational in explaining the origin of the universe, not just in terms of its beginnings, but also in how we think about its boundaries. According to this theory, the universe began as a hot and dense singularity and has been expanding ever since. This expansion continues to this day, and as a result, distant galaxies are receding from us at ever-increasing speeds. The farther away a galaxy is, the faster it appears to be moving away. This relationship, known as Hubble's law, serves as a key piece of evidence supporting the Big Bang Theory. But even as the universe continues to expand, the question remains, what lies beyond it? The Big Bang Theory challenges the very notion of an edge or boundary. As space itself stretches, new regions of the universe come into view. This ongoing expansion suggests that rather than a defined edge, the universe is constantly unfolding, its boundaries continually shifting as we gain new ways to observe the cosmos. As observational technology advances, we can peer deeper into the universe than ever before. However, the farther we look, the more questions arise. What lies beyond the observable universe? Will we ever reach the limits of space, or is there no limit at all? These questions invite us to consider the true nature of the cosmos, a vast, ever-expanding frontier that holds more mystery than we can possibly comprehend. Through the exploration of both theoretical and observational cosmology, we continue to expand our understanding of the universe, pushing the boundaries of human knowledge in the process. The study of the universe, from the Big Bang to the possibility of infinite bubble universes, challenges us to think beyond the limits of our everyday experience. As we continue to delve into the depths of space, we are reminded that the universe is far more intricate, complex, and mysterious than we ever imagined. In the end, our understanding of the cosmos is still evolving, just as the universe itself continues to expand and unfold before our eyes. Furthermore, studying the cosmic background radiation, often referred to as the afterglow of the Big Bang, offers scientists a profound opportunity to explore the early conditions of our universe and gain insights into what it might contain. This radiation is essentially a snapshot of the universe just moments after the initial explosion, and analyzing this relic from such a distant time grants researchers a clearer picture of how matter and energy were distributed in the infant cosmos. It also serves as a guide, helping us understand the ways the universe developed and the structure it has today. Through the lens of the Big Bang Theory, we are allowed a fascinating glimpse not just into the universe's past, but also its present and its unfolding future. Chaos theory, a field dedicated to the study of unpredictable systems that are highly sensitive to initial conditions, has revolutionized our understanding of the universe, particularly at its grandest scales. In the past, scientists believed the cosmos followed predictable laws, much like a vast clockwork mechanism operating in a strictly orderly fashion. However, chaos theory has unveiled a much more nuanced and unpredictable side of the universe. Even in such a vast expanse, elements of unpredictability shape how we model the structure and evolution of the cosmos. At the farthest reaches of the universe, where conventional physics struggles to offer clear answers, chaos theory becomes particularly relevant. This is evident when we observe galaxies, clusters of galaxies, and the cosmic web, an intricate network of matter shaping the entire universe. In these regions, small fluctuations, such as gravitational interactions between celestial bodies, can cause vastly different outcomes in how these structures form and evolve. Chaos theory, therefore, offers a compelling explanation for why two seemingly similar regions of the cosmos can display such starkly different characteristics. It has led researchers to reconsider the perceived stability of cosmic structures. By applying principles of this theory, scientists have come to recognize that what might appear steady and predictable over short timescales is often subject to fluctuations and transformations over much longer astronomical timescales. This insight is reshaping our understanding of fundamental phenomena, such as galaxy formation and the distribution of dark matter. It suggests that chaos plays a central role in the very fabric of the universe. As we peer deeper into the cosmos, the implications of chaos theory remind us of the complexity and mystery of the universe. Understanding these chaotic components enhances our comprehension of cosmic history and evolution, while also urging us to explore the mysteries that lie beyond the limits of our current observational reach. Every chaotic interaction, no matter how small, could hold the key to understanding everything from the birth of stars to the ultimate fate of the universe itself. It is precisely for these reasons that chaos theory has become an essential part of modern cosmology. When we turn our attention to the shape and structure of the universe, we enter a realm of theories that challenge and expand our understanding of reality. One of the most prevalent concepts in cosmology is that of a flat universe, an idea supported by numerous observations suggesting that space is not only vast, but behaves in a uniform manner across large scales. This notion aligns with the theory of an infinite universe, one that extends endlessly, with galaxies scattered throughout it. Yet, in stark contrast, some theorists propose the concept of a closed universe, one that is shaped like a sphere. In this model, if one were to travel in a straight line long enough, they would eventually return to where they started. This theory conjures the image of a finite universe that is nonetheless unbounded, much like the surface of a balloon. It is a thrilling idea to consider. A universe that might curve back upon itself, bending the very fabric of space in ways that are at once familiar and entirely alien. On the other hand, some theorists posit the existence of an open universe which would resemble the shape of a saddle. In this scenario, the universe would continue expanding indefinitely, with galaxies becoming increasingly sparse as time passes. The implications of such a model point to a dynamic, ever-changing cosmos, one that challenges our conventional ideas of permanence and stability. As the universe expands, it transforms in ways that are difficult to predict, pushing the boundaries of our understanding. Adding another layer of complexity to these concepts is the groundbreaking idea of the multiverse theory. This theory proposes that our universe is not the only one. Instead, it is just one of an innumerable number of other universes, each with its own unique structure and set of physical laws. The multiverse theory pushes the limits of our comprehension, suggesting that alternate dimensions and realities could exist beyond our perception. Engaging with these theories allows us to peer into the very fabric of existence, raising profound questions about our place in this vast and mysterious cosmos. It encourages us to rethink not only our universe, but also the nature of reality itself. As we approach the farthest reaches of the universe, we enter a domain where the unimaginable becomes possible. Observations at this cosmic frontier have revealed a tapestry of bizarre and awe-inspiring celestial events, all driven by the extreme conditions found at the universe's edge. One of the most captivating phenomena discovered at these distant locations is the detection of gamma-ray bursts, massive explosions occurring in galaxies far away. These bursts are so powerful that for a brief moment, they can outshine entire galaxies. They mark the dramatic death throes of massive stars, or the catastrophic merging of neutron stars. Another striking discovery near the universe's edge is the existence of quasars, intensely luminous, active galactic nuclei that emit tremendous amounts of energy, often comparable to the collective energy output of thousands of galaxies. Quasars are thought to be powered by supermassive black holes at the centers of galaxies, where gas and dust spiral inward, creating a luminous accretion disk. Observations of these fascinating objects allow astronomers to glimpse the universe as it existed billions of years ago, offering a rare window into the earliest epochs of cosmic history. Then there is the cosmic microwave background radiation, another relic from the time just after the Big Bang. This faint glow, which permeates all of space, serves as a snapshot of the early universe, revealing the conditions that eventually led to the formation of galaxies and stars. By studying this radiation, we have enriched our understanding of cosmic evolution, providing crucial insights into the large-scale structure of the universe and its transformation over time. Each of these discoveries takes us one step closer to unraveling the mysteries of the cosmos and deepening our understanding of the forces that shape the universe we know today. Moreover, the discovery of enigmatic cosmic strings, intriguing, theoretical one-dimensional defects in the very fabric of space-time, points toward phenomena yet to be fully understood. These cosmic strings could stretch across vast distances, potentially serving as cosmic lenses that bend light or influencing the movement of surrounding matter. As our exploration of the universe's edges continues, we remain captivated by these structures, which offer tantalizing glimpses of the cosmic mysteries that still lie waiting to be uncovered. One such mystery lies in the spectacular explosions marking the dramatic end of a massive star's life, supernovae. These colossal explosions hold profound clues about the cosmos and its fundamental limits. When these massive stars exhaust their nuclear fuel, they can no longer support the immense weight of their own gravity. This leads to a rapid collapse, followed by a catastrophic explosion. This cataclysmic event not only scatters a wealth of elements into space, enriching the surrounding environment, but also marks a pivotal moment in our study of the universe's expansion and its underlying composition. The study of supernovae, especially type 1a supernovae, has revealed some of the most significant insights into cosmic evolution. In binary star systems, a white dwarf star can accrete material from a companion star. Once it reaches a critical mass, a sudden ignition occurs, causing an explosion. The consistent peak brightness of these supernovae serves as a standard candle, a vital tool for measuring cosmic distances. By comparing the known intrinsic brightness of these supernovae with their apparent brightness from Earth, astronomers can determine their distance. This method has allowed scientists to calculate the rate at which the universe is expanding. Astonishingly, this expansion has been found to be accelerating, driven by a mysterious force known as dark energy. In addition to revealing the universe's expansion, supernovae provide valuable insights into the limits of stellar mass. The processes involved in these explosive events shed light on the life cycles of stars, how they form, evolve, and ultimately die. As the elements forged within these stars are released into space, they enrich the interstellar medium, fostering the birth of new stars and planets. This ongoing cycle contributes significantly to chemical evolution, forming the very building blocks of life. By observing and modeling supernovae across different galaxies, we gather invaluable data that enhances our understanding of universal principles. The study of these spectacular events pushes the boundaries of our knowledge, continuously shaping our perception of the universe's origins and its ultimate destiny. These violent, awe-inspiring explosions remind us not only of the universe's raw beauty, but also of our own place within it. They urge us to confront deeper questions about existence, transcending the limits of our current understanding. In the vast expanse of intergalactic space, an intricate web of cosmic filaments and voids unfolds, some of nature's most fascinating and perplexing structures. Cosmic filaments, vast structures composed of galaxies and dark matter, stretch across the universe like threads in a giant web. These filaments connect clusters of galaxies, forming a vast, interconnected network that governs the distribution of matter on a cosmic scale. In contrast, the voids, massive expanses of empty space, lie between these filaments, where few galaxies reside. The scale of these structures is mind-boggling, with some filaments stretching across hundreds of millions of light years. One of the most intriguing aspects of cosmic filaments is their influence on galaxy formation. The gravitational pull of these filaments appears to play a crucial role in guiding gas and dark matter toward galaxies, aiding in their formation and growth. This process helps to explain the clumpy distribution of galaxies throughout the universe. However, the exact dynamics at play within these structures are still not fully understood, and astronomers continue to investigate how these filaments impact the life cycles of galaxies over the course of billions of years. The voids themselves, often perceived as empty spaces, are far from devoid of interest. These vast regions provide valuable opportunities for studying dark matter and the large-scale structure of the universe. Some researchers even hypothesize that voids may offer clues to understanding the phenomenon of cosmic acceleration, the force behind the universe's expanding rate. The nature of dark energy, the mysterious force driving this acceleration, may be reflected in the behavior of matter within and around these voids. As technology continues to advance, we are gaining the tools needed to probe deeper into these enigmatic structures. New telescopes and observational techniques are helping us uncover the hidden secrets of cosmic filaments and voids. This growing body of knowledge not only allows us to map the universe's history more accurately, but also enhances our understanding of the fundamental forces that shape everything, from the smallest subatomic particles to the vast cosmic web itself. With each new discovery, we are confronted with the humbling realization that the universe remains full of mysteries yet to be uncovered. Among the most captivating of these phenomena are quasars, or quasar-stellar objects, some of the brightest and most distant objects in the universe. Powered by supermassive black holes at the centers of galaxies, quasars emit vast amounts of energy as material falls into these black holes, forming an accretion disk. As this material is compressed and heated to extreme temperatures, it emits intense radiation across the electromagnetic spectrum, making quasars some of the brightest objects in the sky. Their brilliance allows astronomers to observe them even from billions of light years away. The study of quasars offers vital insights into the distant regions of the universe, particularly in understanding how galaxies formed and evolved over time. Since quasars are often found in the early universe, they act as natural markers for the conditions that prevailed during that epoch. By observing the light from these distant objects, we gain a glimpse into the universe's early history, learning about the interactions and evolution of various cosmic structures across billions of years. In analyzing quasar light, astronomers gather critical data on the distribution of matter, the presence of dark matter, and the rate at which the universe was expanding during its infancy. Quasars thus serve as invaluable windows into the deep past of our universe, offering essential clues about its formation, structure, and the processes that continue to shape its evolution. As we delve deeper into their study, quasars promise to unlock further secrets of the cosmos, expanding our understanding of the universe's grand narrative. The light emitted by quasars, those distant beacons of energy from the farthest reaches of the universe, often passes through the intergalactic medium on its way to Earth. This journey provides researchers with a unique opportunity to study the vast and mysterious matter that exists between galaxies. This intergalactic matter, largely unseen and unexplored, holds critical clues to the very nature of the universe, including its composition, density, and temperature, especially when it was still in its formative years. The study of quasars offers an essential window into the universe's past, giving scientists a deeper understanding of how the cosmos evolved. These objects, often located billions of light years away, are not merely points of light in the night sky. They are, in many ways, time capsules, preserving information about the early universe in a way that no other objects can. Through their light, we can trace the intricate interplay between galaxies and their environments, shedding light on the fundamental forces, energy, matter, and cosmic dynamics that have shaped the universe's large-scale structure over time. Moreover, the information drawn from quasars reveals far more than just their own distant existence. By understanding the way their light interacts with the intervening space, researchers can begin to unlock the secrets of the universe's evolution. Every quasar serves as a cosmic puzzle piece, drawing us ever closer to a more complete picture of the universe's vast history. As we look to these extraordinary objects, they continue to beckon us to explore beyond the boundaries of our galaxy, offering us glimpses into the far reaches of the cosmos. Cosmic inflation, a groundbreaking theory that emerged in the early 1980s, fundamentally reshaped our understanding of the universe's origins and structure. It proposes that shortly after the Big Bang, the universe expanded at an unimaginable rate, growing by a factor so vast in a fraction of a second that the very fabric of space-time itself stretched beyond recognition. This explosive expansion helped smooth out the universe, making it remarkably uniform and isotropic, appearing the same in every direction, despite originating from a single, incredibly small point. Before the concept of cosmic inflation was proposed, astronomers were unable to explain key features of the universe, including the uniform distribution of galaxies and the existence of the cosmic microwave background radiation. Cosmic inflation provided a framework that tied these phenomena together. It posited that tiny quantum fluctuations in the early universe were stretched across the vast expanse of space during inflation, becoming the seeds for the large-scale structures we observe today, such as galaxies and clusters of galaxies. Beyond the large-scale distribution of matter, the theory of inflation has deep implications for our understanding of the universe's boundaries. According to this theory, the observable universe, the part we can see and study, is just a tiny fraction of the whole cosmos. Beyond this observable realm, there may exist regions of space that we simply cannot detect, let alone comprehend, due to the rapid expansion during inflation. This invites the tantalizing possibility that there could be vast swaths of the universe that lie beyond our current observational reach, stretching the limits of both our scientific knowledge and imagination. Cosmic inflation, therefore, paints a picture of a universe far grander than what we can see, a universe that may be infinite in scale. It provides a powerful lens through which we can examine the complexities of the cosmos and its evolution, offering answers to long-standing questions while simultaneously raising new ones. As we continue to explore the farthest corners of the universe, the theory of inflation challenges us to reconsider what we know, fueling an insatiable curiosity about the universe's true nature and pushing us to deepen our understanding of its origins. As we peer into the cosmos, the drive to understand the universe's outermost edges propels ongoing scientific missions aimed at unveiling the mysteries of the far reaches of space. Among the most ambitious projects currently underway is the James Webb Space Telescope, an instrument designed to look deeper into the universe than ever before, offering unprecedented views of the first galaxies to form after the Big Bang. Through its observations, Webb promises to offer new insights into the very fabric of the universe's early history. In addition to Webb, the European Space Agency's Euclid mission stands poised to explore the enigmatic phenomena of dark matter and dark energy. These mysterious forces are believed to govern the expansion and structure of the universe, yet they remain largely undetectable by traditional methods. Euclid will map the distribution of galaxies across vast distances, providing crucial data that could unravel the mysteries of these invisible forces. As these missions continue to push the boundaries of our knowledge, others are also proposed to explore more ambitious concepts in space travel and cosmological research. The Cosmic Explorer Observatory, for example, seeks to detect gravitational waves, ripples in space-time, caused by some of the most violent events in the universe. By studying these waves, scientists can gain new insights into the birth and evolution of the universe, unlocking hidden aspects of cosmic history that are otherwise inaccessible. The very concept of exploring the edges of the universe might seem like the stuff of science fiction, but it is an embodiment of humanity's relentless pursuit of knowledge. With each mission, we draw closer to answering the profound questions that have captivated our species for millennia. These missions not only deepen our understanding of the universe's origins, but also expand our horizons in ways we are just beginning to comprehend. Pondering the vastness of the cosmos and the possibility of venturing beyond its observable limits often feels like entering a realm of pure imagination. Yet, thanks to advances in space exploration, we may one day gain the capability to explore regions of space that now seem impossible to reach. The observable universe currently extends about 14 billion light-years in every direction, meaning that the light we see from distant stars has taken billions of years to arrive at Earth. But what lies beyond this immense distance? Could there be a way to venture beyond the observable universe and explore these uncharted realms? One of the most exciting areas of theoretical research is faster-than-light travel. This concept, which defies the familiar laws of relativity, proposes that space itself could be manipulated to allow for travel faster than the speed of light. The Alcubierre drive, a theoretical framework, suggests that by expanding space behind a spacecraft and contracting it in front, we could create a bubble that moves faster than light without violating the principles of physics. Although this remains purely speculative at present, and would require resources and materials far beyond our current capabilities, it ignites the imagination about what might one day be possible in intergalactic travel. Another promising avenue for the future of space exploration lies in the study of wormholes, hypothetical passages through space-time that could provide shortcuts across vast distances. If wormholes do exist and can be stabilized, they might offer a means to travel between distant parts of the universe in a fraction of the time it would otherwise take. While the existence of wormholes remains unproven, the idea of these cosmic tunnels provides an exciting possibility for future space travel, enabling us to access regions of the cosmos that are currently beyond our reach. In the end, as we explore these fascinating concepts and push the boundaries of what we know, we are reminded that the universe is far more mysterious and vast than we can even begin to imagine. Every new discovery, every new mission, brings us closer to understanding the universe's grand design and the profound forces that shape its existence. The quest for knowledge is far from over, and as we continue to look toward the stars, we will undoubtedly find new frontiers to explore, ever expanding our understanding of the cosmos and our place within it. Advancements in propulsion technology are rapidly transforming our ability to travel within our solar system and beyond. As innovations in ion engines, solar sails, and even nuclear thermal propulsion continue to evolve, they are shaping the future of space travel, pushing the boundaries of what is possible. These technologies hold the promise not only of faster journeys within our solar system, but also of a future in which humanity's ventures into deep space may no longer be confined to the realm of science fiction. With every technological leap, we inch closer to the day when interstellar travel could become a tangible reality. However, it's not just about traveling farther. It's about preparing humanity for an era where space exploration extends beyond the limits of our current imagination. These breakthroughs are redefining what we know about our universe. We are beginning to peel back the layers of space itself, gaining insights not only into the cosmic landscape, but also into the very fabric that binds it together. The dream of exploring realms beyond the observable universe is slowly shifting from fantasy to a plausible future, with each discovery bringing us closer to understanding not just the mechanics of space, but its very essence. As we stand on the precipice of this new frontier, preparing for the unknown is both exhilarating and daunting. The universe, in all its vastness, is a mysterious and intricate tapestry. With each new finding, we are reshaping our understanding of existence itself. Yet, to truly prepare for the journey ahead, we must adopt a mindset of relentless curiosity and openness. The road ahead will be shaped by scientific inquiry, collaboration, and the unwavering desire to seek out the unknown. Encouraging this mindset means fostering a spirit of collaboration across disciplines. Often, breakthroughs arise when seemingly unrelated ideas converge, creating new avenues of exploration. Education plays a vital role in this preparation. By expanding scientific literacy across all age groups, we equip the next generation with the tools they need to engage with new discoveries. This effort goes beyond teaching the fundamentals of cosmology and physics. It also involves nurturing critical thinking skills. By engaging the public in discussions about the cosmos, we demystify these complex topics, empowering individuals to actively participate in the global conversation about our universe. Alongside education, investing in technology and research is crucial. The tools we use to study the cosmos, telescopes, space probes, and satellites, must evolve in tandem with our expanding capacity to observe and measure the universe. As these instruments become more sophisticated, our ability to make unexpected and transformative discoveries increases. Cutting-edge scientists are already working on innovations that will enable us to peer deeper into the cosmos than ever before. Supporting these advancements is essential, for the next breakthrough could come from the most unexpected corners of space exploration. Yet, with these advancements come profound implications. Whether it's evidence of other life forms or new insights into cosmic phenomena, the discoveries we make may challenge our existing beliefs and assumptions. To navigate this new era, we must nurture a mindset that balances skepticism with wonder. Each new discovery brings us one step closer to not only understanding the universe, but also to understanding our own place within it. The process of discovery will be as transformative for humanity as it is for the knowledge we seek. International collaborations are indispensable in the pursuit of space exploration. When nations unite, pooling their resources, expertise, and technology, they often embark on missions far more ambitious than any single nation could manage on its own. These collaborations drive innovation in spacecraft design, data collection, and scientific analysis. The quest to understand the cosmos becomes a collective effort, one that reflects the spirit of exploration and the power of diverse perspectives working toward a common goal. The International Space Station, ISS, stands as one of the most iconic examples of such international cooperation. Orbiting Earth, the ISS serves as a laboratory and research hub, built and maintained through a partnership between space agencies from the United States, Russia, Europe, Canada, and Japan. Scientists from across the globe live and work there, conducting experiments that test theories about bodily functions in microgravity and advance our understanding of fundamental scientific questions. The impact of this collaboration extends far beyond space, enhancing technology and medicine here on Earth. In the same vein, missions like the Mars Science Laboratory and the James Webb Space Telescope demonstrate how international partnerships extend to cosmic exploration. These missions benefit from the contributions of multiple countries and organizations, each bringing unique expertise and specialized equipment. Through collaboration, scientists enhance the quality of data collected and the insights derived from it, expanding the possibilities of discovery. The very fact that many of our most groundbreaking discoveries about the universe are made by teams that span continents illustrates how science transcends borders. These collaborative efforts highlight the shared nature of the pursuit of knowledge, where the drive to understand the cosmos unites nations in ways that go beyond political and geographical divides. In this way, space exploration fosters a sense of shared humanity, demonstrating that the quest for knowledge is universal and that, in the end, we are all part of the same endeavor to uncover the mysteries of the cosmos. As we continue to push the boundaries of space exploration, we must also confront the ethical questions that arise from our discoveries. The very act of venturing into space brings with it a responsibility to consider the impact of our actions on the extraterrestrial environments we encounter. Are we entitled to alter or exploit worlds that may have remained untouched for billions of years? When we send robotic probes to Mars or to icy moons like Europa, we must be mindful of the possibility of microbial life. Even the smallest contamination, whether from microbial hitchhikers or the extraction of resources, could permanently alter these environments. The ethical responsibility tied to planetary protection is also significant. The Outer Space Treaty, signed by many nations, establishes guidelines for the preservation of celestial bodies, recognizing that these worlds are valuable and should be preserved for future generations. This raises profound philosophical questions about stewardship. Are we, as the inhabitants of Earth, the rightful guardians of these distant worlds, or is it our duty to leave them untouched, respecting their natural state? Balancing scientific curiosity with respect for the cosmos is critical. As we venture deeper into space, we must continue to develop thoughtful guidelines to ensure that our exploratory methods do not cause irreversible damage. But the ethical considerations do not end there. The discovery of intelligent extraterrestrial life presents an entirely new set of challenges. If we encounter other civilizations, should we attempt to communicate with them, or should we allow them to remain unaware of our existence? There is a real concern that our arrival could be perceived as intrusive or even threatening, and the manner in which we conduct such contact will require careful thought. As a collective society, we must ask ourselves how to approach these potentially profound encounters. Just as we strive to respect the autonomy and culture of diverse human societies here on Earth, we must apply the same respect to any extraterrestrial civilizations we might find. Navigating this ethical landscape will require humility, wisdom, and an unwavering commitment to ensuring that the pursuit of knowledge does not come at the cost of our shared values of respect, fairness, and stewardship. Exploring the unknown corners of our universe has long been a source of wonder, but it also raises fundamental questions about who should determine the course of such exploration. Space, often viewed as a global commons, is subject to complex politics that can lead to tensions between nations and private corporations seeking to stake their claim. As we launch further into the cosmos, the issue of equity and access becomes central. It is essential that we craft a shared vision for space exploration, one that ensures the benefits are spread across humanity rather than hoarded by a privileged few. By addressing these ethical considerations, we lay the groundwork for a responsible and inclusive approach to our journey into the universe. The question of life beyond Earth stretches our imagination to its limits, urging us to rethink what constitutes life itself. Current scientific theories suggest that just as life on Earth thrives in vastly different environments, it may also exist in far-flung regions of the cosmos. One of the most exciting possibilities is that life could survive in places with conditions that seem inhospitable to us, such as the dark matter halos that encircle galaxies or the freezing, empty stretches of intergalactic space. One hypothesis gaining traction is the idea of extremophiles, organisms that flourish under extreme conditions, whether high heat, intense radiation, or crushing pressures. If such resilient life forms can exist on Earth, could similar organisms survive in the frozen voids of space, or perhaps tap into resources beyond our current understanding? This perspective compels us to explore the harshest, most hostile corners of the universe, expanding our search for life to realms once deemed too extreme. Another tantalizing possibility lies in the search for life on exoplanets, worlds orbiting stars far beyond our solar system. Some of these planets may reside within their stars that habitable zones, regions where conditions might be right for liquid water to exist. The discovery of organic molecules or strange atmospheric signatures could suggest that the building blocks of life are far more widespread than we once imagined. As telescopes and our ability to observe distant planets improve, the likelihood of finding life, whether microbial or more complex, becomes ever more plausible. This search for life is not only about answering an age-old question, but also about understanding the incredible diversity of possible environments in which life could emerge. And then there is the possibility of advanced civilizations, intelligent beings living at the very edge of the universe. If such civilizations exist, they may be using technologies or communication methods far beyond anything we currently understand. This introduces the prospect of interstellar communication, the exchange of information across vast distances, and even the presence of probes or signals that remain undetected by our current instruments. The universe is so vast, and as our understanding of it deepens, we are left to wonder what astonishing discoveries might await us in the farthest reaches of space. In the pursuit of detecting life in extreme cosmic environments, scientists are venturing into some of the most hostile regions in our solar system. The icy moons of Jupiter and Saturn, Europa and Enceladus, are prime candidates for exploration. Beneath their frozen surfaces, vast subsurface oceans may harbor the potential for life. Despite the inhospitable conditions, freezing temperatures and crushing pressures, life on Earth provides hope. Extremophiles here on Earth manage to thrive in the harshest environments, from volcanic hot springs to radioactive waste dumps. Could life in some form endure in similar conditions elsewhere in the solar system? To investigate these moons, scientists employ a range of advanced technologies. Robotic missions equipped with drills and sensors are being sent to pierce the thick ice crusts, enabling researchers to sample the waters beneath. These samples could reveal microbial life or organic compounds, biological markers that suggest life as we know it could exist elsewhere. Spectroscopy, a method used to analyze the composition of materials on planetary surfaces or within geysers, offers another invaluable tool in this search for life. In addition to robotic exploration, the study of Earth's own extreme environments, like deep-sea hydrothermal vents or acidic lakes, provides insight into how life might adapt to the most unforgiving habitats. The quest to find life in these harsh environments challenges our very understanding of biology. It forces us to question how life can endure in places where the conditions seem hostile to all known forms of existence. As technology progresses, the possibility of discovering life, even in the most unlikely places, sparks a sense of awe and wonder about the vastness and mystery of our universe. Each new mission brings us a step closer to answering one of humanity's oldest and most profound questions. Are we alone in the cosmos? Picturing life at the edge of the universe invites us into the realm of the extraordinary, where survival itself would require unimaginable adaptations. At these cosmic fringes, resources would be scarce, and life forms would need to develop incredibly efficient methods to extract energy. With sunlight or chemical reactions impossible, these organisms might rely on cosmic background radiation or the remnants of long-dead stars. This energy harvesting could be akin to how some extremophiles on Earth utilize geothermal energy, but it would operate on a far grander cosmic scale. In addition to energy extraction, these life forms would also have to contend with temperatures and radiation levels far beyond anything we encounter on Earth. To survive, they might evolve protective mechanisms like thick, heat-resistant exoskeletons, or skin capable of shielding them from deadly radiation. Some may even develop the ability to enter a dormant state, suspending their biological processes when faced with extreme conditions, much like certain microbes on Earth endure in the most hostile environments. Communication and locomotion at the edge of the universe would also present new challenges. In an environment where sound and light are ineffective, life forms may develop entirely new methods of interaction, perhaps communicating through chemical trails or manipulating magnetic fields. Instead of using traditional propulsion methods, they might drift through space, harnessing the power of gravitational waves or solar winds. These adaptations stretch our understanding of physics and biology, pushing us to imagine what life could look like in the farthest reaches of the cosmos. The search for exoplanets, planets orbiting stars outside our solar system, remains one of the most fundamental aspects of humanity's quest for life beyond Earth. In this search, we are primarily focused on identifying planets with conditions similar to our own. The ultimate goal is to locate worlds that might be capable of supporting life as we know it. Central to this search is the concept of the habitable zone, the region around a star where temperatures are just right for liquid water to exist. Water is considered essential for life, and its presence on an exoplanet makes it a prime candidate for further study. By identifying exoplanets within their star's habitable zones, scientists can focus their efforts on those worlds most likely to support life. Using powerful telescopes, they examine the atmospheres of these distant planets, looking for signs of life, whether in the form of organic molecules or other biological markers. As technology advances and our ability to observe distant worlds improves, the dream of discovering life beyond Earth grows ever closer. The search for these distant planets is not merely a scientific endeavor. It is a quest to answer one of the most profound questions humanity has ever asked. Are we alone in the universe? Moreover, advancements in technology have significantly expanded our ability to explore the far reaches of space and uncover the mysteries of distant worlds. Telescopes, now equipped with some of the most sophisticated instruments ever designed, allow us to analyze the faintest traces of light emitted by planets as they pass in front of their host stars. This method, known as transit photometry, has proven to be an invaluable tool for scientists. By carefully studying the way light interacts with a planet's atmosphere during this transit, we can detect various chemical elements that might be present. For instance, gases like oxygen, methane, and carbon dioxide, molecules often associated with biological processes, could serve as potential markers of life. Such discoveries are not just of academic interest. They form a growing body of evidence that suggests we may not be alone in the universe. As we continue to discover more exoplanets, the sheer diversity of these worlds has sparked an unprecedented level of excitement within the scientific community. Some planets may exist in conditions so extreme that life as we know it would be impossible. Others, however, could be strikingly similar to Earth, with environments that may harbor life, or at least the conditions necessary for its emergence. Each new exoplanet discovered brings us one step closer to answering one of humanity's most profound questions. Are we truly alone in the cosmos? However, confirming the existence of life on distant planets, especially those located near the outermost boundaries of our galaxy, presents a significant challenge. The regions of space in question are often vast, dark, and inhospitable, making any potential evidence of life extraordinarily difficult to detect. To overcome this, scientists are employing a multifaceted approach to evidence gathering, seeking clues from a variety of sources. First and foremost, the search for biological signatures takes center stage. The discovery of organic molecules, compounds that form the building blocks of life, could provide a vital clue that life exists elsewhere in the universe. These molecules could be found in environments as diverse as the icy moons of gas giants or in the outer regions of our own solar system. The detection of gases like methane, which can often be produced by biological processes, would also serve as a compelling indicator that life might exist in those environments. Beyond organic chemistry, scientists are also focusing on identifying ecosystems that show signs of metabolic activity. This involves the analysis of gases like oxygen, nitrogen, and carbon dioxide, paying particular attention to variations in their concentrations that might suggest biological processes are taking place. Space telescopes, with their ability to probe the chemical composition of distant atmospheres, are crucial in this effort. The ability to detect subtle changes in these gases could be the key to unlocking the secrets of life on other worlds. Furthermore, the search for repeating or structured patterns in environmental data could provide another breakthrough. Patterns that appear too regular or predictable to be the result of random forces might indicate non-random processes that could be consistent with the presence of living organisms. This line of investigation could open new doors to understanding how life might manifest in environments vastly different from those on Earth. Another avenue of exploration is the study of extremophiles, organisms on Earth that thrive in extreme conditions, such as extreme heat, cold, and pressure. If we could find analogous organisms living in similar harsh environments on distant worlds, it would significantly strengthen the case for life's adaptability. Robotic missions sent to these far-flung locations could bring back invaluable samples, which could be tested for biological activity and resilience, further supporting the idea that life can exist in the most unlikely places. Finally, a more speculative but equally fascinating proposition involves the search for signals or technological evidence from intelligent civilizations. Radio signals, laser transmissions, or other forms of communication detected from the far reaches of space could not only confirm the existence of life, but also suggest a level of intelligence. This search for extraterrestrial intelligence, SETI, continues to captivate the imagination of both scientists and the public. If such signals were ever detected, they would represent a monumental leap in our understanding of the universe and our place within it. The evidence required to confirm the existence of life beyond Earth is not likely to come from any one discovery alone. Instead, it would be an intricate tapestry of biological signs, chemical compounds, and potentially even technological evidence that, when pieced together, could unveil the mysteries of life beyond our planet. As we look toward the far edges of the universe, our search for life becomes not just a scientific endeavor, but a journey that speaks to the deepest questions of our existence. As we turn our gaze to the furthest corners of the universe, the very concept of time takes on an entirely new and complex character. In our everyday lives, we perceive time as a constant and linear progression. Seconds tick by at a steady pace, and events unfold in a predictable order. However, the immense scale of the universe and the strange workings of cosmic mechanics challenge this simple understanding. At the extreme distances near the edges of the universe, the way we experience time undergoes a profound transformation. One of the primary factors influencing time in these distant regions is the effect of gravity, as described by Einstein's theory of general relativity. According to this theory, massive objects such as black holes and neutron stars can warp the very fabric of space and time. The closer we get to these massive objects, the more this warping effect becomes pronounced. As a result, time slows down relative to areas farther away. This means that in regions of intense gravitational influence, such as those near black holes or other massive celestial bodies, time could stretch and behave in ways that feel completely alien to our daily experience. As we approach the universe's edge, particularly in areas where gravity has an especially strong influence, the effects on time become even more dramatic. For example, Near a black hole, time would appear to slow down dramatically, creating an experience where events unfold at a pace that seems almost frozen in comparison to our own world. The further we move into the unknown, the more the fabric of space-time itself bends and warps, leaving us with a concept of time that is vastly different from the steady progression we are accustomed to on Earth. This fascinating interaction between space, time, and gravity is just one of the many mysteries that continue to captivate scientists and astronomers as they push the boundaries of our understanding of the cosmos. As we look into the distant reaches of space, we are not merely observing the present, we are witnessing the unfolding of events that happened billions of years ago. The light we see emanating from far-off galaxies has traveled across vast stretches of space, a journey that spans unimaginable distances and lengths of time. This means that the further we peer into the cosmos, the further back in time we are looking. It's as if we're peering through a cosmic window into the past, offering us a kind of visual time travel. Each distant star, each far-flung galaxy holds secrets about the universe's evolution, revealing its history long before humanity's own existence. At the very edge of the observable universe, time itself becomes more than just a sequence of moments. It becomes a dimension, intricately linked to the cosmos, the matter that composes it, and the immense distances between objects. This connection serves as a humbling reminder of how everything in the universe is interconnected. It challenges us to rethink not only how we perceive time, but also our place in the grand unfolding story of the universe. Time dilation is one of the most fascinating phenomena that emerged from Albert Einstein's theory of relativity. Einstein showed us that time does not pass in a uniform way across the universe. It is malleable, and can be influenced by factors such as velocity and gravity. The implications of this become particularly captivating when we consider the vast scales of the cosmos. For example, when we look at stars or galaxies millions or even billions of light years away, the light we're seeing is incredibly old. Yet, if we could somehow travel close to the speed of light, an astronaut aboard a spaceship might experience only a few years of travel, while countless years would pass on Earth. This means that if humans were able to venture out into space at such speeds, their return to Earth would likely find a world vastly different from the one they left behind. Their personal experience of time would differ dramatically from those who remained behind. Similarly, time behaves differently near massive objects such as black holes due to their immense gravitational pull. This is known as gravitational time dilation. Time, in this case, slows down as one approaches a black hole. A clock situated near a black hole would tick more slowly than one positioned farther away. This has profound implications for our understanding of cosmic events. For example, if we were to observe a clock falling into a black hole, from an external perspective, it would appear to slow down, becoming almost frozen. In such extreme conditions, measuring the passage of time becomes a complex challenge, one that forces us to reconsider how we observe the universe and how we define time itself. The concept of time dilation fundamentally challenges our conventional understanding of both time and space. As astronomers strive to measure the vastness of the cosmos, these effects reveal that the universe is not just a boundless expanse, but also a place where the very concepts of time and reality are interwoven with the fabric of space itself. This powerful relationship continues to spark our curiosity, pushing us to ask questions about the true nature of the universe. When we gaze at the stars, we are witnessing not just points of light in the night sky, but rather a vast tapestry of cosmic history woven over unimaginable timescales. Our understanding of this history is shaped by these colossal spans of time, stretching from millions of years to the unfathomable scale of billions. For instance, our own solar system is approximately 4-6 billion years old, yet the universe itself is thought to be around 8 billion years old. This staggering difference helps us place events within the broader narrative of cosmic evolution, giving context to the ongoing story of how the universe has changed and developed. Many of the phenomena we observe in space occur on timescales far beyond the scope of human life. Stars, for example, live out life cycles that can last millions to billions of years. To understand a star's evolution, from its birth in stellar nurseries, through its luminous phases, to its eventual death as a supernova or a white dwarf, requires us to embrace the vastness of these timescales. Each phase of a star's life offers insights not just into the star itself, but also into the formation of galaxies and the creation of the heavy elements that make up the Earth. Likewise, the process of biological evolution, like the evolution of the universe itself, unfolds over immense periods of time. The rise of life on Earth, from the simplest organisms to the complex forms that populate the planet today, is a story that spans billions of years. Understanding this geological and biological deep time allows us to appreciate the complexity and resilience of life, highlighting how much it has been shaped by processes that far exceed the human lifespan. In this context, it is impossible not to recognize the fleeting nature of human existence within this grand timeline. By contemplating the cosmic timescale, we are not only gaining knowledge about the universe's history, but also cultivating a deep sense of awe and respect for the forces that have shaped it. This understanding invites us to rethink our place within the grand continuum of existence. It provides a fresh perspective on how the past, present, and future are all connected, and how the universe continues to unfold in ways that we are only beginning to comprehend. Astronomers use a variety of tools to study the age of celestial bodies, and these age estimates offer invaluable insights into the expansion and evolution of the universe. By determining the ages of stars, galaxies, and other cosmic entities, scientists can create a timeline that helps us understand the universe's development. One of the key methods in this process is the study of globular clusters, dense collections of stars that are often billions of years old. By studying the ages of these clusters, astronomers can glean important information about the rate of expansion during different periods of cosmic history. Similarly, examining the light emitted by distant galaxies provides essential clues about the early universe. Light from these galaxies, which has traveled billions of years to reach us, serves as a kind of cosmic time capsule. By measuring the redshift of this light, its shift toward longer wavelengths as a result of the expansion of the universe, astronomers can estimate the distance of these galaxies and the speed at which they are moving. This data is crucial for understanding how the universe has expanded since the formation of these distant objects. The study of these ancient light sources allows scientists to piece together a clearer picture of the universe's history. Each aged star or galaxy contributes a valuable piece to the puzzle, helping us better understand the nature of cosmic expansion and the formation of the structures we observe today. The more we learn about these distant objects, the more we deepen our understanding of the very fabric of the cosmos itself. Light, in this context, acts as a messenger, carrying information across vast distances. When we observe a distant galaxy, we are not seeing it as it is now, but rather as it was when the light first departed. This phenomenon of light travel time gives us a glimpse into the past, allowing astronomers to trace the evolution of the universe from its earliest moments. When we look at a galaxy that is, say, 10 million light years away, the light we see today left it 10 million years ago. This delay in the transmission of light is crucial to our understanding of the universe's history. This relationship between distance and time enables scientists to estimate the age of the universe itself. By studying the most ancient light known to us, the cosmic microwave background radiation, astronomers have determined that the universe began around 13.8 billion years ago. This groundbreaking discovery provided the first concrete age for the universe, previously thought to be boundless and timeless. The journey of light across the cosmos serves as a cosmic clock, and each photon that travels through space carries with it a piece of the universe's history, illuminating not just the vastness of space, but also the incredible story of how our universe has evolved. As we explore the boundaries of quantum mechanics, our understanding of the universe becomes even more intricate. Quantum theory challenges our traditional notions of reality, particularly when it comes to the universe's boundaries. While we might imagine the universe as an endless expanse, quantum mechanics introduces the idea that particles can exist in multiple states simultaneously, defying the classical concept of clear, separable boundaries. One of the most intriguing aspects of quantum theory is the concept of entanglement, where particles become interconnected in ways that transcend physical distance. This suggests that the universe may not have a clear boundary after all. Instead, all its elements might be part of a vast, interconnected quantum tapestry. The boundaries we perceive could be illusions, with everything in the universe bound together in a complex web of relationships that we are only beginning to understand. This challenges the traditional idea of a finite universe and opens up the possibility that the universe is infinite, or at least behaves in ways that are far beyond our current comprehension. As we venture deeper into the mysteries of the cosmos, it becomes clear that the more we learn, the more our understanding of space, time, and reality itself is reshaped. The universe is not a static, finite entity. It is a dynamic, evolving system in which time, space, and matter are intricately interwoven, and where the fundamental laws of physics continue to inspire our deepest questions about existence. The journey to understand the cosmos is, in many ways, just beginning. Quantum fluctuations add a fascinating, almost mysterious dimension to the vast expanse of the universe. These tiny, spontaneous changes in energy levels can give birth to particles seemingly from nothing. This phenomenon presents a challenge to our traditional understanding of boundaries. If the universe can spontaneously create matter and energy, then the concept of an edge, or even the nature of the universe itself, may be far more fluid and dynamic than we once believed. As such, the universe begins to appear less like a static, fixed space with well-defined limits, and more like an evolving, interconnected system. This shift in perspective prompts a reimagining of the cosmos, an ever-changing network where the interrelation of forces, matter, and energy creates a constantly evolving reality. The convergence of quantum mechanics and cosmology compels us to reconsider the universe not as a cold, unchanging expanse, but as a deeply intricate, fluid system filled with potential for further discovery. It encourages us to ask profound questions about how expansive and intricate the universe really is, and opens up a world of possibilities that far exceed our current understanding. The more we delve into these realms, the more we are reminded of how much we have yet to uncover and explore. In recent years, breakthroughs in theoretical physics have begun to reshape the way we comprehend the cosmos. One of the most groundbreaking concepts emerging from this field is quantum gravity, a framework designed to merge the principles of quantum mechanics with Einstein's theory of general relativity. This fusion of ideas has given rise to theories such as string theory and loop quantum gravity, which suggest that the very fabric of the universe might be far more complex than we can perceive. These theories hint at hidden dimensions and offer tantalizing new insights into the nature of space, time, and reality itself. Another theory that has captivated the scientific community is the concept of the multiverse. This idea posits that our universe may not be the only one, but rather a single thread in a vast tapestry of countless other universes. Each universe may have its own set of physical laws and characteristics. This perspective challenges the assumption that our universe is uniquely fine-tuned for life and invites us to reconsider the fundamental nature of existence. If there are infinite other universes, some of which might be more or less conducive to life, how do we define the essence of our own reality? And what does it mean for our place in this grand multiversal structure? Moreover, advancements in our understanding of dark matter and dark energy are poised to revolutionize our knowledge of the cosmos. These elusive substances are thought to make up roughly 95% of the universe, yet their true nature remains shrouded in mystery. Theoretical physicists are racing to develop models that might explain how dark matter and dark energy influence cosmic structures and the expansion of the universe. Discovering what these enigmatic components are could completely transform our cosmological models, leading to a more complete and accurate understanding of the universe's evolution. And as we continue to explore and refine these theories, the way we perceive the cosmos will shift dramatically. Each new discovery deepens our appreciation of the universe's complexity, reminding us of how much more there is to learn. With every breakthrough, we inch closer to answering timeless questions about the nature of reality, existence, and the very fabric of space and time itself. The discovery of new particles at the edges of the universe holds the potential to dramatically reshape our understanding of physics. For centuries, the field of physics has operated within a framework built on existing particles, fundamental forces, and the laws that govern them. These established principles have allowed us to explain everything from the behavior of atoms to the vast movements of galaxies. However, the universe is vast, and it remains a mystery in many ways. New particles could introduce entirely new concepts and forces that we have yet to consider. One of the most exciting implications of discovering new particles is the potential to redefine our fundamental understanding of matter and energy. Current theories, such as the Standard Model of particle physics, offer explanations for many phenomena, but they leave significant gaps, such as the inability to explain dark matter, which is believed to constitute a large portion of the universe's mass. The discovery of new particles could provide valuable insights into the nature of dark matter, opening up a cascade of discoveries that will illuminate the structure and behavior of the universe itself. The introduction of new particles might also challenge existing notions of physics, leading to groundbreaking theories that unify previously disparate realms of thought. For instance, imagine a theory that bridges the gap between quantum mechanics, which governs the smallest scales of existence, and the principles of general relativity, which govern the vast structures of the cosmos. The discovery of exotic new particles could suggest that these realms are more interconnected than we ever realized. What we once thought of as separate domains of reality, microscopic and cosmic, might in fact be more intimately linked than we ever imagined. In practical terms, the discovery of new particles could lead to a host of technological advancements. As theoretical frameworks evolve, they could inspire innovations in energy production, computing, and even medical technologies. The pursuit of understanding the universe's fundamental components holds the promise of tangible benefits here on Earth, demonstrating that the exploration of the cosmos is not just an academic endeavor, but one that could significantly impact our daily lives. The fundamental forces of nature are the building blocks of everything we observe in the universe. These four forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, play a crucial role in shaping the cosmic structures that we see. Of these forces, gravity is the most significant when it comes to the formation of large-scale cosmic structures. It acts as the glue that binds matter together, pulling together clouds of gas and dust to form stars and planets. Over time, these gravitational interactions culminate in the creation of even larger structures, like star clusters, galaxies, and galaxy clusters. In the early universe, minute density fluctuations, which arose from quantum fluctuations, were amplified by gravity. This process caused matter to clump together, eventually giving rise to the complex and beautiful cosmic structures we see today. Without gravity, the universe would not have taken the shape it has. It is the invisible hand that has sculpted the universe from the very beginning, and its influence continues to shape the cosmic landscape, even in ways we are only beginning to understand. While gravity is undeniably essential to the functioning of the cosmos, it is far from being the only force that shapes the universe. Other fundamental forces, such as electromagnetism, also play crucial roles in the processes that govern the birth and evolution of stars and galaxies. Electromagnetism, for example, controls the interactions between charged particles, which in turn drives the chemical processes that lead to star formation. It is through this force that gas clouds, once subject to the pull of gravity, are able to cool and collapse, forming the very stars that illuminate our universe. Without such interactions, our universe would lack the diverse array of elements needed to form planets and sustain life. The birth of stars, the building blocks of galaxies, is intricately tied to the interactions of electromagnetic forces. In addition to electromagnetism, the weak and strong nuclear forces operate at much smaller scales, influencing the behavior of atoms and subatomic particles. These forces govern processes like nuclear fusion in stars, which not only produce vast amounts of energy, but also forge heavier elements. These elements, in turn, are ejected into space when stars explode as supernovae, seeding future generations of stars and planets. This cyclical process of stellar birth, death, and rebirth is an integral part of the cosmic tapestry, with the fundamental forces working in harmony to create the complexity and richness of the universe we observe. Gravity, the invisible force that governs the motion of celestial bodies, plays a central role in our understanding of the universe. It is the force that dictates the trajectories of planets, stars, and entire galaxies, shaping the large-scale structure of the cosmos. Yet gravity is not merely a force of attraction. It is a relationship, a connection between objects that determines their movement through space-time. A deeper understanding of this fundamental force could revolutionize space exploration. If we were to fully grasp the complexities of gravity, it could lead to new methods of propulsion that allow us to venture further and faster than we ever thought possible. Consider, for instance, the potential of using gravity itself to propel spacecraft. Traditional propulsion systems rely on chemical fuels, which are inherently limited, especially when traveling to distant planets or beyond. However, if scientists could unlock the secrets of gravitational manipulation, it might be possible to develop technologies such as gravity-assisted propulsion systems. These breakthroughs could drastically reduce travel times across vast distances, opening up the possibility of reaching Mars, the outer planets, or even beyond within a human lifetime. The implications for space travel would be profound, making the exploration of the solar system and the universe itself much more attainable. Moreover, gravity is intimately connected to some of the most enigmatic phenomena in the universe, such as dark matter and dark energy. These mysterious forces remain largely unexplained, yet they seem to play a key role in the large-scale structure and expansion of the cosmos. By understanding gravity at a deeper level, scientists may be able to uncover the nature of these unseen forces and how they interact with the matter we can observe. This knowledge could lead to a host of new discoveries, from the identification of potential resources on distant planets to a better understanding of the birth and death of celestial bodies. A clearer understanding of gravity could also open up possibilities for human habitation beyond Earth. With the right knowledge of how gravity operates on different celestial bodies, we could design structures capable of withstanding extreme planetary conditions. This could be essential for colonizing planets like Mars, or for creating long-term human settlements in space. Advances in gravitational research might even enable us to develop life support systems that are better suited to the challenges of living off Earth. Ultimately, mastering gravity could be the key to unlocking the universe's most profound mysteries and securing a future for humanity as interplanetary explorers. Astrophysical observations are at the heart of our efforts to understand the universe's boundaries, often referred to as the observable universe. These observations allow us to piece together a picture of the cosmos based on the light emitted by distant galaxies, supernovae, and the cosmic microwave background radiation. The study of this faint radiation, a relic of the Big Bang, provides critical insights into the early history of the universe. By analyzing this afterglow, astronomers can infer much about the conditions that existed in the first moments of the universe's existence and how it expanded over time. One of the key discoveries enabled by these observations is the theory of cosmic inflation. This idea suggests that the universe underwent a rapid and dramatic expansion just moments after the Big Bang. This inflationary period is thought to have set the stage for the universe's current structure and shape. The study of cosmic background radiation helps to confirm that the universe is not only expanding, but that it has a finite age and a defined, observable extent, determined by the distance light has traveled since the universe's birth. In addition to this, the properties of distant galaxies give us valuable clues about the universe's shape and the way it curves in real space. By observing the movement and distribution of galaxies, astronomers can identify patterns that align with theoretical models of cosmic evolution. For instance, the redshift of light from galaxies moving away from us confirms that the universe is expanding uniformly. This suggests that the universe does not have a physical edge in the conventional sense. Rather, it has a limit to what we can observe, governed by the finite speed of light. These astrophysical observations act as a lens through which we can explore and validate our understanding of the universe's edge. They not only support existing theories, but also open up new avenues of inquiry about what lies beyond the horizon of our observable universe. As our tools and methods improve, we may be able to uncover more details about the farthest reaches of the cosmos, helping us refine our models of the universe's structure and evolution. Large-scale surveys are essential for advancing our understanding of the universe. These surveys, which capture data from millions of celestial objects, provide a sweeping view of the cosmos, allowing scientists to map the distribution of galaxies, dark matter, and other cosmic phenomena across vast distances. This comprehensive data helps us uncover the underlying structure of the universe, revealing patterns that tell us about its architecture and evolution. Through these surveys, scientists have discovered clusters of galaxies as well as voids, vast regions almost completely devoid of galaxies. The distribution of these structures is crucial for testing theories of cosmic evolution, particularly the influence of dark energy, the mysterious force driving the accelerated expansion of the universe. Large-scale surveys provide the necessary data to refine our models of cosmic evolution, offering new insights into how the universe has developed since the Big Bang. As our understanding of the cosmos continues to grow, these observations and surveys will help us answer fundamental questions about the nature of the universe, its origins, and its ultimate fate. By piecing together the evidence from distant galaxies, cosmic radiation, and dark matter, scientists are slowly unraveling the intricate and awe-inspiring story of the universe. Surveys conducted across the vast reaches of the cosmos reveal profound insights into some of the most perplexing elements of the universe. Among these mysteries is the elusive presence of dark matter, which constitutes a significant portion of the universe's mass. While it cannot be directly detected, astronomers can infer its existence by studying the movement and interaction of galaxies. Through this indirect evidence, science has begun to piece together a more complete and intricate picture of the universe's composition and the powerful gravitational forces at work. Large-scale cosmic surveys act as a kind of cosmic lens, revealing not only the visible objects in the universe, but also offering tantalizing clues about the invisible phenomena that shape our reality. As these surveys expand, our understanding of the universe's past, present, and future deepens, raising new questions and propelling us further along our journey through the cosmos. The presence of dark matter is one of the greatest puzzles in modern cosmology. This enigmatic substance neither emits, absorbs, nor reflects light, rendering it invisible to conventional telescopes. Yet, the evidence supporting its existence is overwhelming, particularly in the distant corners of the universe. One of the most compelling pieces of evidence comes from the study of galaxies, where astronomers have observed that the stars within galaxies orbit their centers at speeds far higher than expected if only visible matter were present. This anomaly suggests that an unseen mass, which we call dark matter, is exerting a gravitational influence, keeping galaxies intact and preventing their stars from being flung into space. This gravitational effect is also observed in galaxy clusters. When astronomers map the distribution of visible matter in these clusters, they often find a mismatch between the observed mass and the mass needed to maintain the cluster's stability. Further evidence comes from the phenomenon of gravitational lensing, where light from distant objects is bent by massive foreground objects. This bending reveals the presence of much more mass than can be accounted for by visible matter alone, offering yet another clue to the existence of dark matter. Even more subtle evidence emerges from the cosmic microwave background radiation, the faint afterglow of the Big Bang. Variations in this radiation provide insights into the density of matter in the early universe. Analyses suggest that a staggering 85% of the universe's mass energy content is in the form of dark matter. This overwhelming proportion confirms the critical role dark matter plays in shaping the cosmic structure we observe today. Although dark matter remains hidden from direct view, the mounting evidence for its existence is undeniable and shapes our understanding of the universe's outer edges and beyond. In the ongoing quest to understand the universe, simulations have become an invaluable tool alongside observational studies. While telescopes and other instruments help gather data from the cosmos, Simulations allow scientists to create detailed models of cosmic phenomena that may be impossible to observe directly. These models span everything from galaxy formation to the behavior of black holes, providing a controlled environment where astronomers can test their hypotheses and explore new scenarios. Simulations are particularly beneficial for studying events that unfold over incredibly long time scales. The evolution of the universe, for instance, spans billions of years, a time frame too vast for direct observation. By using simulations, researchers can investigate how various cosmic forces interact over time, offering insights into the underlying physics that govern these processes. This interplay between simulations and observations enhances our understanding of cosmic events, allowing scientists to refine their theories and improve their models. Moreover, simulations provide a framework for interpreting the complex and often ambiguous data collected from cosmic observations. For example, when astronomers analyze light from distant galaxies, the data is often layered with uncertainties. By comparing these observations with the predictions made by simulations, scientists can uncover patterns and glean more information about the galaxies, including their masses, compositions, and velocities. This synergy between simulations and real-world observations helps astronomers to refine their models of the universe, leading to a more accurate and nuanced understanding of the cosmos. In the field of cosmology, inconsistencies in data often serve as breadcrumbs, leading scientists toward deeper insights. These anomalies, which can arise from various sources, whether from telescope observations or satellite data, reveal hidden facets of cosmic behavior or fundamental physics. One striking example is the unexpected dimming of light from distant supernovae, which led to the groundbreaking discovery of the accelerated expansion of the universe. This phenomenon suggested the presence of dark energy, a mysterious force driving the cosmos apart at an accelerating rate. Through a combination of direct observations, theoretical simulations, and the careful analysis of anomalous data, scientists continue to unlock the mysteries of the universe. These insights not only bring us closer to understanding the invisible forces that govern our cosmos, but also open new avenues of exploration, challenging our understanding of the universe's origins and its ultimate fate. Each discovery builds on the last, drawing us ever deeper into the cosmos and reminding us of how much there is still to learn. However, the specifics of dark energy continue to present one of the most perplexing puzzles in contemporary science. These unexpected findings are essential, as they defy established theories and urge researchers to ask new, often profound questions. This constant reevaluation and adjustment of our scientific models lead to groundbreaking innovations and deeper insights into the cosmos. For instance, recent investigations into the cosmic microwave background radiation, the faint echo of the Big Bang, have uncovered inconsistencies. These anomalies suggest that the universe may not be as homogeneous and isotropic as we once believed. In fact, new studies indicate there could be local structures or hidden forces influencing our cosmic landscape, phenomena that remain poorly understood. These revelations challenge our current models of how cosmic structures form and evolve, pushing us to rethink the universe's very shape and ultimate fate. The discovery of such inconsistencies is not a setback, but rather a fertile ground for scientific progress. They call into question the status quo, opening the door to alternative hypotheses that could radically transform our understanding of the universe. Each new puzzling result brings us one step closer to solving the grand enigma of the cosmos, uncovering its hidden complexities, and perhaps its most guarded secrets. It is through this process of continual questioning and revision that we push the boundaries of our knowledge and inch ever closer to revealing the fundamental nature of existence itself. Documentaries on popular science serve an indispensable role in making the vast and often intricate subject of cosmology accessible to the general public. By simplifying complex ideas, these documentaries serve as gateways to the wonders of the universe, allowing viewers of all backgrounds to engage with ideas that were once the domain of experts alone. With captivating visuals and compelling narratives, these films stir the imagination, transforming abstract concepts into something tangible. They introduce audiences to the nature of black holes, dark matter, and the very origins of the universe, sparking curiosity and igniting conversations that extend beyond the screen. The power of these documentaries lies not only in their stunning imagery, depicting galaxies, nebulae, and other cosmic phenomena, but also in the emotional connection they foster. By telling the stories of the scientists behind groundbreaking discoveries, they humanize the scientific process, showing that cosmology is not just about equations and theories, but about real people pushing the limits of what we know. These narratives resonate deeply with viewers, inspiring them to learn more and engage with scientific content outside the documentary. Moreover, interviews with renowned scientists lend credibility to the discussions, providing expert insights that demystify the field of cosmology. When audiences hear directly from those at the forefront of space exploration and research, it transforms the subject from something distant and abstract into a dynamic, human-driven quest for knowledge. These documentaries do more than educate. They inspire viewers, creating a ripple effect that can lead to deeper community engagement, new educational initiatives, and a long-lasting passion for understanding the universe. By bridging the gap between cutting-edge science and everyday comprehension, these films cultivate a lifelong curiosity about the cosmos, helping us all explore our place within it. When we think about the universe, many of us imagine an infinite expanse with a definite edge, much like a map. However, one of the most common misconceptions is the belief that the universe has a physical boundary, a point beyond which there is nothing. In reality, current scientific models suggest that the universe is not only expanding, but might be infinite, meaning that it does not have a sharp, definable edge. Instead, the universe is more accurately described as a continuously evolving, curved space that stretches without a clear limit. This brings us to another misconception, the idea that you could simply travel far enough to reach the edge of the universe. This notion is misleading, as space itself is expanding. As you move through it, the distances between galaxies only grow larger. Even if you could travel at the speed of light, you would never reach a boundary. The universe, in this sense, is akin to an ever-expanding balloon. You're always moving away from the surface, but you can never find an edge. Furthermore, people often visualize the universe as a two-dimensional surface with boundaries, much like a flat plate. In contrast, modern cosmology suggests that our universe may be four-dimensional, meaning that it does not conform to the conventional rules of three-dimensional space. This perspective leads us to the concept of the observable universe, which is limited by the speed of light and the universe's age. Because light takes time to travel, we can only see a fraction of the universe's full extent. What lies beyond this observable limit remains beyond our reach, further complicating our thoughts on what the edge of the universe might be. Lastly, another prevalent misconception is that the universe is static. For centuries, it was believed that the cosmos remained unchanged, like an eternal backdrop. However, we now understand that the universe is dynamic, constantly evolving over time. From the birth of stars to the formation of galaxies, change is an intrinsic feature of the cosmos. This revelation fundamentally alters our perception of the universe, urging us to embrace its vast, ever-changing nature, rather than search for a definitive, finite endpoint. As our understanding of cosmology continues to grow, so too does our awe and wonder about the mysteries that lie beyond, prompting us to continue exploring this grand cosmic puzzle. Filmmakers possess a unique ability to transport audiences to the farthest reaches of the universe, making the complex science of cosmic exploration both captivating and accessible. One of the most effective tools they use is breathtaking visual imagery. With high-quality computer-generated graphics and real space footage, they bring the wonders of the cosmos to life, depicting swirling galaxies, distant planets, and cosmic phenomena in ways that not only dazzle the eyes, but also stir the imagination. When viewers watch these awe-inspiring scenes, they are not merely witnessing stunning visuals, they are emotionally engaging with the very vastness of space itself. In addition to stunning visuals, storytelling plays a critical role in translating the complexities of space exploration into something relatable. By weaving narratives around historical missions and the scientists behind them, filmmakers humanize the scientific journey. These stories of ambition, struggle, and discovery make the science feel personal, connecting the audience to the people who have dedicated their lives to unlocking the secrets of the universe. For example, a documentary might follow the journey of a spacecraft, showing not only the technical challenges it faced, but also the excitement and triumphs of its findings. This approach personalizes the science, turning it into a quest that spans generations. Moreover, expert commentary from astronomers, physicists, and engineers can break down the often daunting concepts of space science into simpler, more digestible ideas. This expert input allows filmmakers to explain intricate topics like black holes, dark matter, and the nature of time itself in ways that are both engaging and understandable. By making complex theories accessible, these documentaries ensure that viewers not only learn, but develop a deeper, more meaningful connection to the field of cosmology. They demystify the universe, showing us that the wonders of space exploration are not just for scientists, but for anyone with a curious mind and a sense of wonder. Curiosity has the extraordinary power to ignite the imagination. When filmmakers embrace this quality, they unlock the potential to spark a deeper connection between audiences and the vast mysteries of the universe. By daring to ask fundamental questions about the origins of life, the possibility of extraterrestrial worlds, or the nature of cosmic phenomena, documentaries push viewers to reflect on their place within the vast expanse of the cosmos. These thought-provoking inquiries, filled with wonder and awe, do more than entertain. They inspire a greater appreciation for the ongoing exploration of the universe that surrounds us. At the heart of this exploration lies science communication, which serves as an essential bridge connecting complex scientific concepts with the general public's understanding. It turns intricate ideas about stars, galaxies, and cosmic theories into engaging, accessible narratives that resonate with everyone. In a time when scientific literacy is a powerful tool, it becomes crucial for people to engage meaningfully with developments in science, technology, and policy. Effective science communication empowers individuals to comprehend and participate in these crucial conversations. By sparking curiosity, science communication fosters a culture of questioning, discovery, and engagement. It encourages individuals to ask the big questions and seek out knowledge in new and innovative ways. This drive to learn doesn't only exist within academic circles. It permeates the media, from documentaries and articles to public lectures and interactive exhibits, designed to pique interest and inspire exploration of the night sky and beyond. When these platforms connect with people, they do more than inform. They create a sense of collective adventure, inviting others to embark on this grand journey of discovery. Clear, concise communication also plays a crucial role in dispelling misconceptions. In a world where misinformation is rampant, science communication has the power to offer clarity. By presenting scientific findings in straightforward, relatable ways, it demystifies topics such as astronomy and physics, making them accessible to all. More than that, it reinforces the importance of the scientific method, emphasizing the value of critical thinking. This approach teaches people how to evaluate sources, question claims, and form informed opinions, helping to create a more discerning public. Successful science communication goes beyond enhancing public understanding. It nurtures a collective sense of responsibility for the planet and its place in the universe. As individuals become more informed about the complexities of the cosmos, they develop a profound appreciation for the beauty and challenges that science brings. This deeper connection can inspire communities to champion scientific endeavors, advocate for educational initiatives, and ensure that the wonders of the universe are explored and safeguarded for future generations. A well-informed public is also crucial in transforming the landscape of funding and support for scientific research. When people understand the profound importance of astronomical inquiry, its ability to answer fundamental questions about existence, they are more likely to advocate for increased funding and resource allocation. This, in turn, can have a ripple effect at the governmental level, where informed citizens elevate scientific discussions in political arenas, ensuring that space exploration remains a priority. Public interest in cosmic phenomena often leads to the growth of educational programs and outreach initiatives, which further enhance awareness about the value of astronomy. These efforts highlight not just the field's intellectual appeal, but its practical benefits to society. People increasingly recognize that breakthroughs in space exploration can lead to innovations that improve life on Earth. Technologies such as satellite communications, weather forecasting, and even medical advancements have their roots in astronomical research. When these connections are made clear, public support for science is bolstered, with individuals advocating for policies and funding that propel these discoveries forward. Moreover, a well-informed public is more likely to engage in philanthropic endeavors and private funding initiatives. People who grasp the significance of astronomical research are well-positioned to be catalysts for change, whether through leading campaigns, contributing to crowdfunding efforts, or participating in community science projects. Individuals can actively support and elevate scientific inquiry. This grassroots support provides an essential avenue for financial backing, complementing governmental funding and fostering a more sustainable ecosystem for scientific discovery. In this interconnected world, the role of the public in supporting and advancing scientific exploration cannot be overstated. As curiosity grows, so too does the collective will to explore, understand, and protect the universe that shapes our lives. Through science communication, we bridge the gap between the stars and the people, creating a future where exploration, innovation, and discovery are celebrated and sustained for generations to come. Public engagement with astronomy has the power to foster a culture of curiosity, exploration, and wonder, sparking an essential shift in how society views the universe. This shift, in turn, inspires future generations of scientists, policymakers, and advocates who champion the pursuit of scientific inquiry and elevate the value of cosmic knowledge. As society places more importance on understanding the cosmos, we can expect a ripple effect, a momentum that propels sustained funding and comprehensive support for astronomical research. An informed populace does more than amplify the demand for financial investment. It creates an ecosystem ripe for scientific discovery, one that nurtures new breakthroughs and fosters an environment of intellectual exploration. Philosophy plays a crucial role in shaping how scientists understand their work and ultimately the nature of reality itself. For centuries, philosophers have asked profound questions about existence, knowledge, and the universe. Questions that continue to prompt scientists to delve deeper into the fundamental principles that govern everything from subatomic particles to the vast expanse of galaxies. The dynamic relationship between philosophy and science encourages a rigorous examination of what it means to know something. What are the limits of human understanding? And what methodologies can we use to uncover deeper truths about the world? One classic philosophical debate, the tension between determinism and free will, provides a striking example of how these questions influence scientific inquiry. If everything in the universe is determined by the laws of physics, what does this mean for our sense of agency and the predictability of events? These profound reflections compel scientists not only to ask how the universe works, but also why it functions in such a particular manner. Such inquiries guide the development of new theories, inform experimental designs, and directly influence the course of scientific progress. Moreover, philosophical perspectives often challenge scientists to confront the broader implications of their discoveries. Take, for example, the discussions surrounding parallel universes or the nature of time. These speculative ideas demand that scientists not only scrutinize the technical aspects of their research, but also reflect on the ethical dimensions and philosophical ramifications. Issues arising in genetics, artificial intelligence, and other rapidly advancing fields require a deep consideration of the societal impact of scientific progress. Here, the intersection of philosophy and science offers invaluable insights, enriching both disciplines and pushing the boundaries of what we can understand about the universe. The role of speculative concepts in shaping scientific thought cannot be understated. These ideas, though often at the fringe of established knowledge, serve as a catalyst for rich and dynamic scientific discussion. When scientists, thinkers, and visionaries imagine possibilities beyond our current understanding, they challenge existing theories, driving the expansion of our comprehension of the cosmos. Concepts like the multiverse, the idea that our universe is just one of many, prompt debates about the very fabric of reality, compelling scientists to reconsider the fundamental laws of physics. These speculative ideas spark curiosity, generating questions and avenues for exploration that might not have emerged in more conventional scientific discussions. Speculative concepts also inspire new methodologies and technological advancements. For instance, while the idea of warp drives, faster than light travel, remains firmly in the realm of theoretical physics, exploring its implications encourages researchers to push the boundaries of propulsion systems, energy manipulation, and other related technologies. This interplay between imaginative speculation and practical exploration can lead to groundbreaking innovations that may one day allow us to venture deeper into the cosmos. Such inquiries challenge scientists to reimagine the future, driving forward-thinking technological advancements that could revolutionize space exploration. Additionally, engaging with speculative ideas can help bridge the gap between various disciplines. Philosophical questions, literary fiction, and even art often intersect with scientific inquiry, offering a broader, more holistic perspective on the universe. By considering the philosophical implications of their findings, scientists enrich their research, while writers and futurists, through imaginative works, help shape the narrative of our future understanding. This cross-pollination of ideas fosters collaboration across disciplines, sometimes leading to unexpected insights and discoveries. These speculative discussions not only challenge the boundaries of what we know, but also connect with our intrinsic human desire to understand our place in the universe. In exploring these speculative ideas, we return to the fundamental questions of existence. What lies beyond space? Are we truly alone in the cosmos? These ideas inspire the search for answers, fueling our motivation to continue exploring, questioning, and expanding the horizons of science. Through speculation, we not only imagine new possibilities, but also draw closer to uncovering the deepest mysteries of the universe. Cosmology, the study of the universe's origins, evolution, and eventual fate, provides insights that extend beyond the confines of scientific examination. At its core, cosmology invites us to confront profound philosophical questions about our place in the cosmos. As we explore the vastness of space and the array of cosmic phenomena, we are inevitably led to ponder existential questions. What does it mean to exist? Why are we here? These questions echo the philosophical inquiries that have shaped human thought throughout history, offering a timeless connection between science and the search for meaning. As we gaze upon the night sky, we don't just see distant stars and galaxies, we see the manifestation of human curiosity and imagination. The discovery of cosmic structures, like black holes, dark matter, and the cosmic microwave background radiation, reveals not just the workings of the universe, but the deep interconnectedness of all things. For many, this knowledge instills a sense of humility, as we are reminded of the smallness of our existence in relation to the vast, intricate cosmos. These realizations provoke introspection about humanity's role and responsibility in this grand, ever-expanding arena of the universe. As astronomical research continues to unfold, so too does our understanding of our place within the universe, a journey that is equal parts scientific, philosophical, and existential. The exploration of space, far from being an isolated pursuit, invites us all to join in a collective search for knowledge, pushing the boundaries of human understanding while questioning the very fabric of reality. This ongoing quest, rooted in curiosity, imagination, and discovery, reminds us that the universe is not just a place to explore, but a mirror reflecting our own deepest questions and aspirations. Moreover, as cosmological discoveries continue to advance, they pose new challenges and enrich the cultural narratives that shape our understanding of existence. Different societies, each with their own distinct mythologies, have long held unique interpretations of the cosmos, offering insights into how humans have envisioned their place in the universe. Yet as science steadily uncovers more about the vastness of space and the intricate workings of the universe, these ancient stories don't have to be left behind. Instead, they can coexist with the empirical knowledge we acquire, evolving into a more holistic understanding of existence that bridges the gap between science, spirituality, and philosophy. This interplay, Where the hard facts of scientific discovery meet the introspective nature of human thought, has the potential to lead us toward a deeper, more nuanced view of reality. It pushes us to consider not just how the universe operates, but what it means to be part of such an immense and complex system. Each discovery, whether it's an answer or a new question, opens fresh avenues for contemplation, reminding us that science is not merely a tool for analyzing the physical world. It also stirs our imagination, inviting us to reflect on the very fabric of existence and our role within it. As we venture further into the vastness of the universe, we inevitably encounter profound philosophical dilemmas that challenge not only our scientific assumptions, but also our very understanding of who we are. Perhaps the most pressing of these questions is whether the universe itself has an edge, or if it stretches endlessly, both in space and time. If the universe is finite, what lies beyond its boundaries? Such questions naturally lead to existential reflections. Are we alone in this vast cosmos, or might there be other worlds, perhaps beyond our reach or understanding, teeming with life? These questions stir deep curiosity, prompting us to reflect on our place in the grand scheme of things. Another major dilemma centers on the concept of time. As we explore the limits of the universe, we're forced to confront questions about its origins and its potential end. If the universe had a beginning, what came before that moment? Did time exist before time itself began? These reflections not only push the boundaries of cosmological science, but also raise larger philosophical inquiries about the nature of creation itself. They invite us to consider the possibility of a creator or an inherent purpose driving the cosmos, urging us to examine our ethics, beliefs, and the moral implications of life in a universe that often seems indifferent to our existence. In parallel with these existential dilemmas, the question of observation and perception becomes critical. As we push the limits of our understanding, we must confront the fact that our observations of distant galaxies and cosmic phenomena are constrained by the speed of light and the limitations of our technology. This leads to an essential philosophical question. Does what we cannot observe truly exist? Furthermore, how do our perceptions of the universe shape our understanding of reality? And how do these perceptions influence our belief systems and worldviews? Ultimately, the limits of the universe serve as a reminder of our own limitations as human beings. We are but a tiny speck in an unfathomably vast cosmos, which can elicit both a sense of humility and a drive for exploration. This dual awareness of our vulnerability and our curiosity encourages us to continue the quest for knowledge while also fostering a deeper recognition of the interconnectedness of all things in the universe. As we look to the stars and ponder the infinite, we are reminded of the immense beauty and mystery that surrounds us, urging us to keep exploring. In the intersection of science and philosophy, speculative thought has long pondered the possibility of alternate realities. Speculative philosophy, with its emphasis on asking what-if questions, challenges us to reconsider our most fundamental assumptions about existence and reality. Thinkers like David Lewis have explored the idea of modal realism, suggesting that all possible worlds, every conceivable scenario, are just as real as the one we inhabit. This framework invites us to imagine alternative outcomes and realities, where the slightest change in the course of events might create an entirely different world. For example, if one small decision, perhaps a fleeting choice made long ago, had been different, could it have sparked a completely new reality? What if entire universes are birthed from every moment of decision, each one splintering off from the other in ways we cannot perceive? Such speculative philosophies find a fascinating intersection with modern physics, particularly in the realm of quantum mechanics. The many worlds interpretation of quantum physics aligns with this idea, suggesting that every quantum event causes the universe to split, leading to the existence of multiple coexisting realities. The union of speculative philosophy and scientific exploration has sparked a wave of imaginative inquiries about the nature of existence. These ideas, while abstract, invite us to grapple with profound questions about fate, free will, and the overall structure of the cosmos. As these concepts trickle into popular culture through films, books, and even video games, they resonate deeply with our innate curiosity. They challenge us to think beyond what we know, to envision a universe teeming with possibilities, each one a different thread in the vast tapestry of existence. The blending of speculative thought and scientific discovery compels us to reflect on what is, what could be, and what might lie beyond the edges of our current understanding. As humanity stands on the cusp of exploring extraterrestrial environments, we face a multitude of ethical dilemmas that require us to think critically about our role beyond Earth. One of the primary concerns is the potential for contamination, both from Earth to other celestial bodies and vice versa. Introducing earthly microbes or organisms to other planets could disrupt or even annihilate any native ecosystems that might exist, forever altering these environments in ways we cannot predict. Scientists are aware of this risk and have advocated for stringent planetary protection protocols that aim to preserve both the integrity of extraterrestrial ecosystems and the safety of our own world. Another pressing ethical issue arises from the possibility of encountering extraterrestrial life, particularly intelligent beings. Should we come into contact with such civilizations, questions of respect, agency, and ethical treatment would immediately come to the forefront. Just as we grapple with the ethical treatment of animals and human rights on Earth, so too would we need to extend this moral inquiry to other sentient beings. What responsibilities would we have in the face of extraterrestrial life? Should we attempt to communicate? And if we do, should we intervene in their development or merely observe? These dilemmas force us to reflect on our values as a species. They challenge us to reconsider what it means to be human and how we should conduct ourselves as we venture beyond the familiar confines of our planet. In the vastness of space, where we are but a fleeting presence, the ethical choices we make may define not only our legacy on Earth, but also our place within the larger cosmic order. As humanity looks to the stars, there are increasing practical considerations surrounding the exploitation of resources in space. Minerals such as cobalt, titanium, and other precious substances found on asteroids or moons promise wealth, but they also raise a host of ethical concerns. The allure of tapping into these extraterrestrial riches is undeniable, yet it triggers a profound debate about the morality of extracting resources from celestial bodies. This act might mirror the exploitative practices seen during Earth's colonial histories, stirring concerns over the potential for new forms of exploitation. The ethical question here is not just about whether we can exploit other worlds, but whether we should. In our pursuit of cosmic riches, we must tread carefully, avoiding the same mistakes that have harmed cultures and ecosystems throughout history. As we venture into these foreign realms, the stewardship of these celestial bodies must be at the forefront of our considerations. It is essential to ensure that, in seeking to utilize these new environments, we do not repeat the injustices we have inflicted upon our home planet. Beyond the matter of resources, the search for extraterrestrial life is perhaps the most profound challenge to our understanding of existence and humanity's place in the universe. Each new discovery, whether it's the detection of distant exoplanets or signs of microbial life, forces us to reconsider not only our scientific models, but also our philosophical and religious frameworks. The discovery of life beyond Earth would prompt a profound reassessment of what it means to be human and our responsibilities to life in all its forms. These scientific revelations do more than just expand our knowledge. They force us to confront deep existential questions about our identity and our future. The discovery of a potentially habitable planet could inspire hope, filling us with the excitement of new possibilities. However, this hope could also carry with it an underlying anxiety as we grapple with the significance of such a discovery and the weight of the responsibility it entails. Are we prepared to handle the implications of finding life elsewhere? And how will that shift our understanding of ourselves? Moreover, working on the cutting edge of scientific discovery often brings with it emotional and psychological fluctuations. Researchers may experience moments of profound joy when a breakthrough is achieved, only to face despair when their work encounters setbacks. The emotional toll can be heavy, and often researchers find themselves isolated, bearing the pressure of high expectations. Yet, the collaborative nature of modern scientific endeavors offers a form of support. Sharing struggles and triumphs with colleagues can help mitigate feelings of isolation, providing a network of solidarity in the pursuit of knowledge. As researchers delve deeper into the cosmos, the psychological impact of their discoveries is complex. On one hand, the awe-inspiring vastness of the universe can evoke a sense of wonder and humility. On the other, it can also lead to existential questions that challenge not only their work, but also their place in the universe. The sense of being part of something much greater than oneself can be both uplifting and overwhelming, pushing researchers to reconsider their priorities and the implications of their findings for humanity's future. This feeling of awe is also the fertile ground in which ethical debates about extraterrestrial life and resources are planted. As we consider the possibility of life on other planets or in distant galaxies, we must ask ourselves, what rights would these life forms have? If intelligent life were discovered, capable of thought and communication, how would we relate to them? Would they deserve the same protections and respect as life on Earth? This question pushes us to examine the ethical frameworks we apply to other living beings, regardless of whether they exist in our biosphere or beyond. If we encounter life in environments that are vastly different from Earth, there will also be new considerations about habitats and ecosystems. Should these life forms live in environments that are unique to their worlds, would we have the right to alter those environments for our own benefit? The destruction of alien ecosystems for resource extraction or colonization would raise serious ethical concerns. It would highlight the necessity of adopting a philosophy of stewardship rather than one of domination. Our technological advances should not come at the expense of these delicate environments. Instead, we should strive to protect them and respect their inherent value. In fact, the very discovery of alien life could shift our understanding of life itself. It might encourage us to broaden our sense of kinship, uniting us with all forms of life, terrestrial or otherwise. Recognizing that life, in whatever form it may take, has inherent value could lead to a more compassionate approach to how we interact with not only Earth's life forms, but potentially those across the universe. This shift in perspective might even prompt a reevaluation of our ethical responsibilities toward the life we share our planet with, encouraging us to treat all life with the dignity it deserves. The exploration of resources beyond Earth brings with it both incredible possibilities and deep ethical concerns. As we venture into space, we must approach these challenges with caution, guided by a sense of responsibility, collaboration, and long-term vision. Celestial bodies such as the Moon, asteroids, and even Mars are home to untapped resources that could provide critical materials for life on Earth, including rare minerals and water. However, the extraction of these resources must be approached with a mindset of sustainability, ensuring that our actions in space do not lead to unforeseen consequences for the future. International cooperation will be essential in navigating the ethical and logistical challenges of space exploration. Space is a shared frontier, and no single nation should lay claim to celestial bodies. The framework established by the Outer Space Treaty of 1967 provides a basis for peaceful exploration, discouraging conflict over space resources while promoting collaboration. By fostering partnerships between nations and private entities, we can pool our knowledge and resources to ensure that space exploration benefits all of humanity. This collaborative approach will be key in ensuring that the wealth of space is shared equitably, advancing scientific knowledge without sacrificing ethical integrity. As we look to the stars and seek to understand our place in the vast universe, the choices we make today will shape the future of space exploration. These choices, rooted in respect, responsibility, and collaboration, will not only determine how we interact with the cosmos, but also how we view ourselves as stewards of life, both here on Earth and beyond. The future of humanity in space depends on the wisdom with which we approach these challenges, ensuring that we move forward in a way that respects both the wonders of the universe and the rights of all forms of life. In our quest to explore the far reaches of the cosmos, ethical considerations must be at the heart of our journey. As we aim for the Moon, asteroids, and other celestial bodies, it is vital that we prioritize the preservation of these untouched environments. These distant landscapes, untouched by human hands, are fragile ecosystems that could be forever altered by even the smallest amount of interference. To avoid irreparable damage, we must create and adhere to strict guidelines for responsible resource extraction. The mistakes of the past, where the exploitation of natural resources led to the degradation of Earth's environment, must not be repeated in our exploration of space. At the same time, we must take a long-term approach to space exploration. It cannot simply be a frantic race for resources. It must instead be a deliberate, strategic effort designed to safeguard the future of generations to come. By investing in technologies that minimize our environmental impact and focusing on renewable resources found beyond our planet, humanity can chart a course for a new era. This is an era in which we make use of the universe's bounty, not at the expense of our own planet's future, but in a way that ensures the sustainability of both Earth and its inhabitants. To achieve this, we must pursue a balanced, ethical, and cooperative approach as we move forward in our ventures into the cosmos. As humanity embarks on this monumental journey to uncover the mysteries of the universe, scientists are entrusted with a profound responsibility. Above all, they have an unwavering duty to pursue knowledge with integrity. This means conducting research with the highest ethical standards, reporting findings honestly, and allowing the quest for truth to guide their discoveries rather than personal or political agendas. Every breakthrough, whether it involves the discovery of the smallest particle or the vast stretches of deep space, carries implications that extend far beyond human curiosity. It impacts our understanding of our place within the greater universe and our relationship to it. Furthermore, scientists bear the crucial responsibility of making their findings accessible to the broader public. The complexity of scientific concepts can often feel daunting to the untrained mind, but it is the scientist's duty to translate these ideas into terms that are not only understandable but engaging. By doing so, they foster a sense of wonder and curiosity about the natural world, sparking a greater appreciation for the universe. This, in turn, inspires future generations to pursue careers in science, ensuring that the search for knowledge remains an ongoing journey, fueled by fresh perspectives and innovative ideas. Another key responsibility that scientists face is the awareness of humanity's potential impact on the cosmos. As we launch spacecraft and delve deeper into the study of celestial bodies, we must be conscious of the far-reaching consequences of our actions. Space debris, for example, poses an ongoing threat to both existing space missions and to the very environment we are exploring. Planetary contamination is another serious issue that scientists must actively work to prevent. It is imperative that we adopt a mindful approach to space exploration, one that emphasizes stewardship not just of Earth, but of the entire universe. Our actions in space must be guided by a deep respect for the delicate balance of the cosmic ecosystem, recognizing that even our smallest actions can have profound ripple effects throughout the universe. Finally, scientists must advocate for sustainability on Earth itself. Understanding the vastness of the universe and the delicate balance of cosmic systems only highlights the importance of caring for our own planet. The lessons gleaned from studying the far reaches of space can be applied to the environmental challenges we face here on Earth. By adopting policies that promote sustainability and encouraging behaviors that protect our planet's resources, scientists can help create a future where humanity exists in harmony with the natural world. In fulfilling their role as stewards of both knowledge and the Earth, scientists can contribute to a future in which our relationship with the universe is not one of exploitation, but of respect and stewardship. When it comes to conveying the complex and often abstract concepts of cosmology, storytelling is an invaluable tool. One of the most effective techniques for making these ideas more accessible is through the use of analogies. By relating vast cosmic phenomena to familiar everyday experiences, scientists can make the unimaginable tangible. For instance, comparing the expansion of the universe to a balloon inflating offers a simple yet powerful way to illustrate how galaxies move further apart over time. These analogies serve as bridges between the known and the unknown, helping listeners grasp ideas that would otherwise be difficult to comprehend. Personal narratives and anecdotes also play a key role in making science more relatable. By sharing the stories of pioneering scientists like Edwin Hubble and his groundbreaking observations that reshaped our understanding of the universe, Listeners can connect with the human element of discovery. These stories humanize the science, reminding us that behind every scientific achievement is a person who faced challenges, made sacrifices, and ultimately changed the way we see the world. These narratives not only inspire curiosity, but also serve as reminders of the perseverance and dedication that drive scientific progress. Visual storytelling, too, is an essential tool in bringing the cosmos to life. Whether through vivid descriptions of swirling galaxies or the intricate movements of celestial bodies, imagery can evoke awe and stimulate the imagination. By painting a picture of the universe, of nebulae shimmering with color, of stars being born, of planets orbiting distant suns, we help listeners visualize the grandeur of space. This visual dimension enriches their understanding and deepens their connection to the vastness of the cosmos. In sum, the future of space exploration rests not only on the technologies we develop, but also on the ethical framework we build to guide us. It requires a collective commitment to knowledge, sustainability, and responsibility, ensuring that as we reach for the stars, we do so with a profound respect for the universe and all it encompasses. Through ethical action, effective communication, and a deep awareness of our impact, we can ensure that humanity's journey into the cosmos is one of wonder, discovery, and respect. The power of storytelling lies in its ability to create a pathway for audiences to navigate complex ideas. By starting with foundational concepts and progressively layering more intricate details, the narrative allows listeners to build their understanding at a pace they can follow. This method ensures that even the most curious minds can keep up with the journey through the cosmos, gradually developing a deeper appreciation for the vastness and complexity of our universe. It is through this structured approach that we can effectively engage the mind, guiding it through both the known and the unknown. At its core, storytelling is a tool that sparks curiosity, especially when it comes to unraveling the mysteries of the cosmos. It provides a framework through which abstract and often bewildering concepts can be transformed into relatable human experiences. By intertwining cosmic phenomena with elements of character, conflict, and resolution, stories invite listeners to embark on an adventure. They are no longer passive recipients of information, but active participants, encouraged to ponder the vastness of space and the enigma of existence itself. Imagine, for instance, a narrative centered around a dedicated astronomer. This character spends countless nights gazing at the night sky, captivated by the twinkling stars above. Their passion for discovery mirrors our own innate desire to explore the unknown, to venture beyond the boundaries of our understanding. As the story unfolds, we learn of their trials, their moments of triumph, and their unwavering commitment to uncovering the secrets of the universe. We, the listeners, begin to feel a deep connection with them. Their curiosity becomes our curiosity, their yearning to uncover the cosmos's mysteries, a shared human experience. Through this personal angle, the facts and figures of the universe are not just data points or dry information. They are transformed into stories that ignite our curiosity, pushing us to wonder not just about what we know, but about what we do not yet understand. This desire to unravel the unknown becomes more than an academic pursuit. It becomes a deeply emotional journey. In addition to this, storytelling often weaves in elements of wonder and suspense, drawing listeners further into the narrative. Think of the awe invoked when black holes are described as monstrous cosmic whirlpools, or when the possibility of life on distant planets is explored. These vivid portrayals of the unknown set our imaginations ablaze, stirring within us a deep sense of wonder. Questions naturally arise. How do black holes form? What might life look like on an exoplanet orbiting a distant star? By framing scientific ideas within these narratives, we are compelled to question and investigate, celebrating the quest for answers alongside the characters we've come to care about. Ultimately, storytelling serves as a bridge between science and emotion. It reminds us that behind every scientific breakthrough, there are people, dreamers and explorers, who dared to ask questions and push boundaries. Whether it is the birth of stars, the formation of galaxies, or the mysteries of dark matter, these stories resonate with us because they engage both our minds and our hearts. Stories about the universe don't just inform us, they inspire us, instilling a lifelong curiosity about the cosmos and our place within it. The history of cosmic exploration offers a rich tapestry of insights that illuminate not only humanity's quest for knowledge, but also our understanding of human nature. It teaches us important lessons about perseverance, collaboration, and the unwavering drive to seek answers. One of the most profound of these lessons is the power of curiosity. From the moment ancient civilizations first gazed at the night sky, they were driven by the same questions that fuel modern scientific inquiry. What are those distant stars? What lies beyond the reaches of our understanding? The urge to explore the cosmos reflects a deeply ingrained human instinct, a desire to seek answers to life's biggest questions. Alongside this curiosity, history teaches us the value of collaboration. The space age, which began in the mid-20th century, saw nations coming together in pursuit of a common goal: to explore the final frontier. The Apollo missions, for example, were not solely the accomplishments of the United States. They were the result of international expertise, talent, and resources working in tandem. These collaborations have demonstrated time and again that when multiple minds come together, they can achieve extraordinary results, pushing the boundaries of what was once thought possible. The challenges faced during cosmic exploration have also provided important lessons in resilience and adaptability. Every mission, from the early days of rocket experiments to the sophisticated rovers currently exploring Mars, has encountered setbacks. These failures, however, are not seen as defeats, but as vital learning experiences. Each misstep serves as a stepping stone, providing invaluable lessons that inform subsequent missions and lead to improved technologies and methodologies. In this way, the history of exploration teaches us that progress is rarely linear. It is often a winding path filled with obstacles, but each challenge brings us closer to the next great discovery. Lastly, the historical narrative of cosmic exploration compels us to reflect on our ethical responsibilities. As we venture further into space, it is crucial that we consider the implications of our discoveries, not just for humanity, but for the future of our planet. The exploration of other worlds forces us to confront questions of sustainability, resource management, and environmental stewardship. As we recognize our interconnectedness with the universe, we must also acknowledge our role as caretakers of Earth, ensuring that our progress does not come at the expense of the planet that sustains us. The story of our journey into the cosmos is not just one of scientific achievement. It is a narrative that challenges us to reflect on our values and responsibilities as we continue to push the boundaries of exploration. Visuals play a critical role in these stories, especially when dealing with the often abstract and intangible concepts found in cosmic discoveries. The universe, in all its grandeur and complexity, can be an overwhelming place, one that is difficult for the human mind to fully grasp. But through high-resolution images captured by powerful telescopes, animations, and illustrations, these vast, intricate details are brought to life. These visuals serve not only to draw the audience in, but also to clarify and simplify complex ideas, making them more accessible and relatable. Take, for example, the stunning photographs of galaxies captured by the Hubble Space Telescope. These images, filled with vibrant colors, intricate spiral shapes, and breathtaking features, evoke a sense of wonder and connection to the cosmos. They are not merely decorative, they help us visualize the scale and complexity of cosmic phenomena, things that words alone often fail to convey. These visuals make the abstract tangible, giving us a glimpse of the universe's immense beauty and sparking within us a deep sense of curiosity. In this way, visuals and storytelling work hand in hand, guiding us through the vast, often mysterious expanse of the cosmos, making the unknown more familiar and reminding us that our journey is just beginning. Visual aids, such as infographics and diagrams, play a crucial role in simplifying complex data presented during the course of cosmic discoveries. When scientists delve into explaining the formation of stars or the behavior of black holes, these visual tools transform intricate theories and numbers into easily digestible formats. They offer a bridge between abstract scientific concepts and the public's understanding, enabling us to grasp phenomena that would otherwise remain beyond our reach. For example, a visual representation of the formation of a star can break down the chaotic, multi-layered processes into a sequence of digestible steps, making the concept more accessible. These visuals do more than just illustrate data. They create a vivid narrative of cosmic events. They help audiences to visualize not only how things happen in the universe, but also why they matter. Without these representations, many cosmic phenomena would remain intangible, locked away in theoretical equations. Infographics allow the viewer to transcend the limits of daily human experience and step into the grandiosity of the universe. They offer a window into the mysteries of space, engaging the imagination and making the vastness of the cosmos feel a bit more familiar. Ultimately, visuals serve as a critical tool in storytelling, especially when it comes to scientific topics like cosmic discoveries. By combining imagery with narrative, they make the science behind our universe not just understandable, but also captivating. This combination turns what could otherwise be dry, abstract knowledge into an inspiring and enlightening journey. When presented with these tools, science becomes an engaging adventure, rather than a series of cold, impersonal facts. In the rich tapestry of scientific discovery, certain figures shine brightly as icons of curiosity, resilience, and relentless pursuit of knowledge. These individuals stand as beacons of inspiration, not just because of their groundbreaking work, but because of the challenges they overcame. Among these luminaries is Albert Einstein, whose theory of relativity forever altered our understanding of space, time, and gravity. Despite facing early academic struggles, Einstein refused to conform to the expectations of his time. His work not only reshaped scientific thought, but also demonstrated the power of questioning the status quo. His life reminds us that true breakthroughs often arise from the willingness to think differently and defy conventional wisdom. Another figure whose work continues to inspire is Marie Curie, the first woman to win a Nobel Prize and the only individual to ever receive Nobel Prizes in two distinct scientific fields, physics and chemistry. Her pioneering research on radioactivity not only advanced atomic science, but also shattered the glass ceiling for women in science. In an era when women were often excluded from scientific endeavors, Curie's groundbreaking achievements sent a powerful message about the importance of dedication, and perseverance in the face of adversity. Her journey is a testament to the transformative power of knowledge and the unyielding spirit of inquiry. Equally inspiring is the legacy of Carl Sagan, an astronomer and science communicator who popularized the field of cosmology. Through his iconic television series Cosmos, Sagan captured the public's imagination, presenting complex scientific concepts in a way that resonated deeply with ordinary people. His belief in the importance of understanding our place in the universe was a cornerstone of his philosophy. His famous words, "We are made of star stuff," encapsulate the profound connection between humanity and the cosmos, reminding us of our origins and our shared existence with the universe. Lastly, the remarkable story of Katherine Johnson, an African-American mathematician, stands as a powerful reminder of the necessity of diversity in science. Johnson's contributions to the early success of the United States space program were pivotal, and her calculations were instrumental in ensuring the accuracy of trajectory paths for astronauts. In an era when racial and gender discrimination were rampant, Johnson's brilliance illuminated the path forward. Her story underscores the idea that diversity is not merely a value, but a critical component of scientific progress. It reminds us that innovation thrives when different perspectives are brought together, enriching the field with fresh ideas. These figures, Einstein, Curie, Sagan, and Johnson, show us that through passion, resilience, and a deep love for discovery, we can overcome even the most formidable obstacles. They inspire us to push forward, to challenge what we think we know, and to never stop searching for answers. Their stories remind us that the pursuit of knowledge is not a solitary endeavor, but a shared journey that transcends time, borders, and barriers. As we look to the future, the search for evidence at the edge of the universe holds the potential to revolutionize our understanding of the cosmos. Imagine standing on the precipice of the known universe, peering into the vast, uncharted territories that stretch beyond our sight. What might we discover? What could we learn that would confirm or challenge our current theories about the origins, structure, and ultimate fate of the universe? These discoveries would not only transform cosmology, but could also profoundly reshape our philosophical and cultural perspectives on existence itself. One of the most profound implications of such discoveries would be the possibility of new physics. If evidence were found that contradicts current models, such as the widely accepted Big Bang theory, it could compel scientists to rewrite the fundamental laws that govern reality. This potential for new frameworks could have far-reaching consequences, sparking an era of innovation and collaboration as scientists work to unravel the mysteries of time, space, and the forces that shape the universe. Imagine how our understanding of the very fabric of reality could evolve, forever changing how we think about time and space. Furthermore, such a discovery could reignite interest in space exploration. The idea of venturing into the unknown would no longer be a purely scientific endeavor, but a cultural rallying cry that could unite nations in a common purpose. As we reach beyond the limits of what we can observe, the search for what lies beyond the edge of the universe could inspire a new era of space missions. Governments, private organizations, and space agencies around the world might invest more heavily in exploring these frontiers, driven by a shared commitment to knowledge. These efforts could not only advance our technological capabilities, but also forge global partnerships, making the quest for discovery a unifying force for humanity. In the end, the search for the unknown at the edge of the universe represents not just a scientific challenge, but a philosophical one. It beckons us to consider our place in the grand tapestry of existence, to confront the mysteries of the cosmos, and to recognize that the pursuit of knowledge is a journey that belongs to us all. The discoveries we make about the cosmos, especially as we push the boundaries of our knowledge, have the potential to resonate with us on a deeply philosophical level. Evidence of interconnectedness or the immense diversity of cosmic phenomena could challenge long-held beliefs about humanity's uniqueness. It might open a window to new perspectives, urging us to confront the reality that we are not alone in the universe and that we are part of something much greater and more mysterious than we had previously imagined. Such revelations could stir a profound sense of humility and wonder. As we recognize our small yet significant place in the vastness of space, a sense of awe emerges, reminding us of the grand complexity that surrounds us. This realization would ignite a spirit of curiosity and an unyielding desire to explore the unknown. The search for knowledge, driven by this curiosity, would not only fuel scientific progress, but also deepen our appreciation for the universe itself. The concept of the universe's edge, or the limits of our cosmic horizon, holds powerful implications. As our understanding of what lies beyond the observable universe evolves, it challenges us to reevaluate our position in the cosmos. This ever-expanding understanding fosters a sense of humility, reminding us that despite our advanced technological achievements, we are still just a tiny speck in the vast cosmic landscape. Such insights would likely inspire future generations to adopt a mindset of exploration, critical thinking, and inquiry, values that are essential for scientific advancement and personal growth. With this new understanding, future generations may view the universe not as a fixed and static backdrop, but as a dynamic, ever-changing entity. This shift in perception could foster a deep sense of interconnectedness among humanity, emphasizing that, despite the seemingly insurmountable distances between us, we are all bound by a common cosmic fate. The awareness that the universe is not merely a collection of stars and galaxies, but a vast, possibly infinite expanse, could inspire a more global and universal outlook on life, one that transcends national borders and cultural divides. Moreover, as we delve deeper into the mysteries of the cosmos, our understanding of the universe's boundaries could reshape our ethical and philosophical views. New discoveries could prompt questions about the very nature of existence, consciousness, and our responsibility, not just to one another, but also to our planet and beyond. These reflections could pave the way for a future where humanity adopts a mindset of stewardship toward Earth and the cosmos alike, viewing our actions on this planet as intrinsically linked to the larger universal framework. In essence, the pursuit of understanding the universe's edge is not simply a scientific endeavor, but a key to shaping the aspirations and dreams of future generations. As we continue to push the boundaries of our knowledge, we are forced to reconsider what it means to be human in an ever-expanding cosmic context. This process could redefine our very identity, pushing us to think beyond the confines of our own world and to connect with something far larger than ourselves. Cosmic discoveries also have the remarkable ability to drive technological advancements here on Earth, often in ways we never expect. As we seek to understand the universe, we uncover fundamental principles that lead to new technologies. For example, the quest for knowledge about space has spurred innovations in materials science, telecommunications, and computing. The challenges associated with space exploration demand robust solutions to complex problems, resulting in technologies that ultimately make their way into everyday life. Take, for example, the development of satellite technology. Initially, satellites were designed for astronomical research and communication, but today, they are the backbone of global positioning systems, weather forecasting, and disaster management. Similarly, space agencies have pioneered cutting-edge technologies like radio telescopes and imaging devices, which have revolutionized the way we gather and analyze data on Earth. The advancements in global communication and internet technology can be directly traced to the need to transmit vast amounts of data from space back to Earth. Furthermore, the drive to create sustainable energy sources has spurred innovations rooted in astrophysics. By studying the energy production mechanisms of stars, such as nuclear fusion, scientists are gaining insights that could eventually help us harness cleaner and more efficient energy on Earth. Research into the extreme conditions of space also leads to the development of advanced materials that are lighter, stronger, and more efficient, benefiting industries ranging from aerospace to manufacturing. Cosmic exploration doesn't just challenge our intellectual capacity, it sparks creativity and ingenuity. When humanity reaches for the stars, it inspires scientists and engineers to think beyond the limits of current technology, resulting in innovations that improve life here on Earth. This creative spirit, born of the desire to explore the unknown, becomes a vital catalyst for progress, driving solutions to some of the most pressing challenges we face on our home planet. The societal implications of new astronomical discoveries can be vast and profound. Imagine, for instance, the moment when we discover definitive evidence of life beyond Earth, or when we identify an asteroid that poses a threat to our planet. Such discoveries could radically shift how we view our place in the cosmos, urging us to reconsider our relationship with the universe and our responsibilities within it. To prepare for these potential paradigm shifts, we must cultivate a culture of curiosity and adaptability. We should foster open dialogue about the implications of new cosmic knowledge and encourage education in science and astronomy from an early age. By making these fields accessible to everyone, we equip people with the tools they need to engage meaningfully with the discoveries we make. Public forums, initiatives that encourage citizen science, and community outreach can help integrate individuals into the ever-unfolding narrative of astronomical exploration. Ethical considerations will also play a crucial role in how we respond to new cosmic findings. The question of how to approach potential contact with extraterrestrial life is just one example of the moral dilemmas we will face. As we learn more about the cosmos, we will need to create frameworks for addressing these ethical challenges. Additionally, new technologies born of space exploration could raise questions about their impact on society, and we must be prepared to deliberate thoughtfully on how to implement these innovations responsibly. International collaboration will be essential as we continue to explore the universe. Partnerships between countries in the field of astronomy allow for the sharing of knowledge and resources, enriching the global conversation about our discoveries. By working together, we create a more united approach to managing the societal changes brought about by new findings, ensuring that our collective response is thoughtful, inclusive, and beneficial for all. As we look toward the farthest reaches of the universe, the discoveries made there will undoubtedly reshape humanity's narrative in profound ways. The edge of the universe represents not just a physical boundary, but a frontier of understanding that challenges our very perception of reality. Each new revelation, whether it's uncovering ancient galaxies or observing the moments just after the Big Bang, provides new insights into the origins of the cosmos and our place within it. These discoveries could either affirm or challenge our current understanding of the universe, pushing humanity to rethink fundamental questions about time, space, and the forces that govern the cosmos. Ultimately, the search for cosmic knowledge will not only shape our understanding of the universe, but also our understanding of ourselves. As we continue to unravel the mysteries of the cosmos, we become more aware of our smallness, yet also our profound significance in the grand narrative of existence. This awareness could inspire unity, collaboration, and peace as humanity collectively faces the challenges and opportunities that come with our expanding knowledge. The technological innovations that arise from our pursuit of understanding the universe's edge will undoubtedly have far-reaching consequences for life on Earth. From advancements in communication and healthcare to breakthroughs in energy production, the knowledge gained from exploring the cosmos will transform our world in ways we may not yet fully comprehend. This dynamic relationship between space exploration and technological progress reminds us that the quest for knowledge is not just about understanding the universe, but also about enriching life here on Earth. The discoveries we make on our cosmic journey could fundamentally alter not only our scientific narrative, but the very essence of what it means to be human.